let's say we wait 2 3 minutes from now.
Yes, yes.
People are connecting, yeah. Sasha, did you have a chance yesterday to see my talk? Because we have
no, unfortunately not.
Okay.
I'm going to see it on YouTube. By the way, is the recording available or?
Yes. So we have a YouTube channel. You can find also information on the webpage of the workshop. So there are recordings. Some of them I already added descriptions. Some of them are just are not. I will add it maybe, but I mean when the workshop ends. So because it takes some time. I mean, first they are live streamed and then they are saved. It takes some time for YouTube to save them, and once it happens, yeah, I will add. I
see. I was citing your work, Sasha. That's why I was asking you. Just to let you know.
That's very kind of you. Sorry, I really wanted to listen to your talk, but I have a student which is going to defend his thesis, and we were discussing that last minute changes in his work.
No worries, no worries.
Sorry for that.
I'm just saying because really overlap with what you are presenting, okay? So I just want to be aware, okay?
Mm-hmm.
Okay, good. 1 more minute and then we go, okay? Okay. So, okay, this goes for Sasha and for all the speakers. I will let you know once you've been speaking for 30 minutes. In that moment, you decide whether you want to finish in that moment and take 10 minutes questions, or of course you can carry on for another 5 minutes, but then you shorten your questions slot in 5 minutes, okay? Just to let you know. If we want to be Swiss precise with time. I'm gonna put my timer here. Yeah. Okay, cool. Guys, should we start?
Yes, let's start.
Okay, great. So welcome everybody. It is a great pleasure to continue with the workshop. This is a Thursday afternoon session. And our first speaker is Chiara Sobol, who is going to tell us about a very interesting technique they have developed to follow nonlinearities in gauge field production during axion inflation. So please, Chiara, go ahead.
Thanks a lot, Danny. Thanks a lot for the introduction. First of all, I would like to thank you for organizing such a wonderful event, this workshop, and also for giving me an opportunity to present our results here. It's a very big honor and pleasure to be here today. So, and I'm going to talk about a new technique, which is gradient expansion formalism, which we apply to describe the gauge field production during axion inflation. This work was done in collaboration with Kai Schmidt from University of Münster and also Stanislav Vinchinsky and Eduard Horber from Taras Shevchenko National University of Kyiv. And it was published last year in these 2 works. Okay, so here is the outline. I will first start from problem of magnetic fields in the universe, then go to the axial coupling model, why it is so important, then a few words about Schwinger effect, the main part about the formalism itself, and then I will conclude. So as we all know, the universe is magnetized at all possible scales, starting from planets, stars, neutron stars, where magnetic fields are pretty large, to galaxies and galaxy clusters where they are for the microgauss, but still they are there. And moreover, since 2010, we know that there is a sort of evidence that magnetic fields are also present on cosmological scales, so in cosmic voids. However, the magnitude of this field is uncertain, so it may lie in this range, and maybe the last few years will show which exactly the value is. So this is a very quick summary of what people know about that, different constraints on the magnitude of magnetic field and its correlation length, lambda b. And so we have two types of constraints, from above and from below. From below is well known, this 2010 observation, the lack of gamma radiation in GeV range from distant lasers. And from here follows that they should be, on very large scale, they should be greater than 10 to minus 16 Gauss. This is like an estimate. And constraints from above are from the distortions of the CMB power spectrum, from Faraday rotation, and a very important, very recent observation, which was reported in the end of the previous year, is from the deviation of ultra-high energy cosmic rays. They limit the value on large scales to 10 to minus 10 Gauss. Okay, so the problem is how to explain this magnetic field, and also the problem is how to explain the magnetic field in the astrophysical object, because we know that different types of dynamo, they work in astrophysical objects, but all of them, they have homogeneous equations. So if we put 0 at the beginning, we get 0 later. So we have to produce some seed feeds for this dynamo mechanism also in astrophysical objects. And the problem is where these seed fields are generated. There are two groups of theories. First one is astrophysical, so they may be generated during the structure formation by some battery phenomena, for example, Biermann battery, and then these fields were amplified in astrophysical objects. They remained inside, and also due to some overflows, they were spread into the void. This is the first group of theories, and the second one is cosmological generation. So they may arise at some early stage of the universe evolution, for example, during inflation, reheating, or different kinds of phase transitions. And then they just evolve in time, and in voids we see what remained. And in astrophysical objects, they were amplified additionally. So, but if the cosmological theories are correct, then these magnetic fields, if we will have a possibility to measure them with better accuracy, their characteristics, they could be another source of information about the early universe, because they come from that ancient time. And today I will focus on the second option, namely the cosmological evolution, and consider the possibility of inflationary generation of such gauge fields. But there is a problem, because the expanding universe is described by the Friedmann metric, which is conformally flat. And since during inflation we do not have any matter field, we do not have particles, so we have only three, for example, gauge field Lagrangian, and it is conformally invariant. If we substitute this into the action, we get the action in Minkowski space-time. And we know that, but only in rescale coordinates and in conformal time, we have just the picture of Minkowski space-time. And that's the problem, because in Minkowski, gauge fields are not generated just by themselves. And the conclusion maybe is that we need to violate this conformal invariance in order to get some amplification. And how to violate it? For example, to couple gauge field to the inflaton. What else can we do during inflation? To couple the gauge field to the inflaton. And another problem arises here, because we know that for successful inflation, and successful, I mean that it should solve all these problems, horizon problem, flatness problem, and so on, we need sufficiently flat potential of the inflaton. And this flatness is maybe destroyed. So if we introduce some coupling between inflaton and gauge field, for example, then some radiative correction may break this flatness and spoil inflation. And only if this there is some symmetry which protects this flatness, for example, the shift symmetry, as it was proposed in the natural inflation model, for example, then we are safe, so we do not spoil this flatness of the potential. And the type of interaction which is shift symmetric is the axion type interaction, because you know, if you put here a constant, this is a full derivative, full divergence, and it doesn't change the equations of motion. So axion inflation model seems to be a very good compromise between we break the conformal invariant and we do not break the shift symmetry. And we will call phi axion. However, it is not like a QCD axion or other. It is like axion-like field. It is some pseudo-scalar field. And the immediate consequence of this term is that it gives a current, an effective current in the Maxwell equation, which is proportional to magnetic field, with alpha being a pseudo-scalar. It is the time derivative of our axion. And by the way, we already know at least two systems that the same form of current appears. The first one is the chiral magnetic effect, of course. So if we have a plasma with different number densities of left and right particles, so there is a chiral asymmetry. This alpha is proportional to the, so to mu pi, to the chemical potential, or to the difference, since it is the proportionality sign. And this is a pseudo-scalar quantity as well. And another example is mean field dynamo theory. You know, when you have some fluctuations, small scale fluctuations of velocity, and some turbulence, where such correlator V curl V is non-zero, this is pseudo-scalar, it breaks parity, then the alpha effect works, and alpha effect gives the same, has the same implication. So we have the growth of the magnetic field. So these two systems are already studied very well. So here we have analogous situation. Yeah, so, but not only the magnetogenesis is interesting when we are talking about axion inflation. For example, here, as I said, such such current leads to tachyonic instability, and only one circular polarization of our gauge field is simplified. So we have a helical gauge field. But not only gauge fields are interesting. Also, people show that gravitational waves are also helical, and which are generated during axion inflation. And also, there are some characteristic features in non-Gaussianity, so in scalar power spectrum. Also, this model provides the effective reheating of the universe after inflation. And last but not least, we produce helical magnetic fields during inflation, but then after inflation, they can decay and produce baryon asymmetry of the universe due to the chiral anomaly. It was also discussed in the literature. So this model has very rich phenomenology, and in order to solve any of these problems, to consider any of these problems, we need to know actually the time dependence of inflaton field, of generated gauge field during inflation. Also, we would like to know the spectrum. And all this can be easily done only in the case if we do not have any back reaction or, for example, Schwinger effect. So what is Schwinger effect? It is a well-known thing. So we produce gauge fields which have magnetic and also electric components. And this electric component can produce, when it exceeds this threshold value, it may produce particles and antiparticles, so produce pairs. And the plasma is forming, it back reacts the evolution of the gauge field itself. So this is a very important phenomenon which we also have to take into account. Analytically, it can be studied, so the Schwinger pair production in application to cosmology, it was studied only in the simplest cases, namely, since we want, so Kobayashi and Hayashinaka and co-authors, they studied the cosmological Schwinger effect only in the presence of electric field. But here we have both electric and magnetic. Therefore, I am citing article of Valerie Domcke and co-authors. So it was purely de Sitter, constant and collinear, very important electric and magnetic fields, and the strong field regime, which means electric field much greater than Hubble, and or the time which we need to create a particle, the pair of particle to particle, is much smaller than the characteristic Hubble time. So in this case, there is a quite simple expression for this induced current, and we will use it. Although we know that during inflation, it is not exactly de Sitter, they are not exactly collinear. However, all these approximations are more or less okay, because we showed that indeed they are very close to collinearity. So in our approach, we use this expression, and moreover, we say that it can be written in the effective form or generalized ohmic form. So we use this Schwinger current as usual Ohm current, where the sigma depends on our electric and magnetic fields generated. Okay, so now we have the full system of equations for this model. So we have the pseudoscalar inflaton field, we have free gauge field, we have axion coupling, and we have this charged field, which we describe phenomenologically by using only the Ohm law. And here are our equations of motion. So this is Friedman for the universe expansions, like Gordon for evolution of axion, Maxwell equations, and also phenomenological. We just write down equation for charged particles, which is just the energy conservation. What is dissipated from electric field, it goes to produce particles. And here we have, so if, for example, these terms, these green terms, are negligible in those two equations, this means, and also produce particles, this means that we can consider background separately. So we can solve for inflaton dynamics, and then using the known values of inflaton, put it into Maxwell equation and solve them. And this was the standard mode-by-mode approach, which was used in the literature since long time ago. So, but it works only if there is no back reaction and no Schwinger effect. Then we, as I said, solve the ground equations. And Maxwell equations can be written for the vector potential in the Fourier space. And here we see that indeed different polarizations, they have different signs here. When the first term dominates, our mode is quickly oscillating. And when the second term starts dominating, then for one of them, we have the minus sign here. So remember, eta is negative. So for plus, we have the tachyonic instability, and one mode grows exponentially. Another one does not grow, it even decays a bit. So we see that, clearly see that we generate helical magnetic gauge field. And then we can solve this equation for all relevant modes, then integrate over the spectrum and obtain electric magnetic field. So that was the standard approach. But it breaks when we have back reaction and Schwinger effect, because these phenomena are highly nonlinear. They couple all modes one to each other. We cannot consider separate modes anymore. So in order to deal with this problem, we introduce another approach. We do not go to the Fourier space. We work in coordinate space, and we introduce the following set of quantities. These are correlators of E, B, B, B with different power of spatial curls here. And we know equations of motion for E and B. Just substituting, we derive equations of motion for these quantities. The plus is, the positive feature is that these are ordinary differential equations in time. So we do not have spatial dependence here. And the minus is that it is an infinite system. The quantity n, in its equation of motion, we have a quantity of n+1 order, and so on and so forth. So we traded an infinite number of Fourier modes for an infinite set of scalar functions. And what do we gain? And the gain is that we can truncate the system to keep accuracy and truncate the system at some finite order and to get the result. So, by the way, here on the right-hand side, we also have some additional terms, which are called boundary terms. And the reason for their appearance is the following. as I discussed just a few slides ago here, that modes for which this first term dominates, so eta, it goes to zero, from minus infinity to zero during inflation. So for any mode, there would be some period of time where the first term dominates, but then when eta comes sufficiently small, the second starts dominating. And the regime of evolution changes. So you can see here before, so when the first term dominates, it is just oscillation, and the absolute value of the mode function is just 1. So no generation is here. But therefore, we will exclude all modes for which the tachyonic instability is not occurred yet. That is why we put here not plus infinity as we usually do when we integrate over the spectrum, but some cutoff. This is adaptive cutoff because it depends on time. And this is the problem because this integral has variable upper limit. And we have the inner time dependence here in the spectral density, and it is taken into account by the left-hand side of this equation. So this is completely described, but this time dependence is not taken into account. That is why we introduce this boundary term, just taking the derivative with respect to time fitting here. And I do not give the expressions, but they can be computed in terms of some special functions, but without big problem. Okay, and the only problem is to truncate the system, as I said before, because it is infinite, and we can do it by a simple observation. So any quantity of this E, B, or G is some integral. Here we have increasing power of k, so we have n power n plus 4. If n is very big, then we can conclude that this integral doesn't matter how this behaves. This integral, we will find such big number of n when the integral will be dominated by its upper limit. Therefore, we can just do the following substitution, and this helps us to truncate the system. And here you see the result. If you truncate at first order, second, third, and so on, so you see that the curves, the black one is the exact solution, and these curves, they approach the exact solution when we increase n maximum. And here is the relative error. You see that it decreases, and at some point it stops decreasing. It stabilizes at a very small value of order 0.5%, which is very good accuracy. And so from here, we conclude that our results do not depend on the truncation order. So this error is not due to truncation, is due to some approximations that we used when derived this boundary terms and so on. But I mean, this relative error of 0.5% is more than enough for all phenomenological applications. Okay, so now we can easily study the back reaction regime. We just, however, for back reaction regime, you see, we need more equations. So this n is 115, and we get the stable solution until the very end of inflation. Yeah, so by the way, in the back reaction regime without Schwinger effect, the results were obtained already by Valerie Domcke and co-authors in this paper, and our method reproduces them perfectly, so they just coincide. And we also recover all the qualitative features, so the inflation is extended. You see that is where inflation ended without gauge fields, and here when it ends, when we include this gauge field. Again, the consistency check shows that the error is of order a few percent, and this is for rather big value of coupling constant. Yeah, so in the regime of back reaction without Schwinger effect, it works perfectly and no problem occurs at all. But there are still a few questions in the case when we include Schwinger effect, because we start from that assumption that I did earlier. So this Schwinger current is an approximation, and we do not know how to improve it. For example, we have to somehow take into account that fields are not collinear, and also maybe we can represent it as some function, some effective conductivity times E plus another conductivity times B, and this would give to would lead us to another theory and give us another result. So this is still what we are working on, but already what we can see that the presence of finite conductivity, it damps our modes, our gauge field modes, which are still inside the horizon, which are oscillating. So before we assumed that when the mode crosses the horizon and joins to the physically relevant mode, it is of order unity, because it is like Bunch-Davis vacuum. So this exponent in Bunch-Davis vacuum, its absolute value is of order unity. But now it is damped due to the presence of conductivity. So the modes which join us are already exponentially damped in time. And moreover, this damping depends on prehistory. So of course, this is an idealization. It is we put here minus infinity, so the whole history. Here we do not take into account that maybe some modes with extremely large momenta, they do not feel conductivity like the static conductivity. We should put here some dynamical conductivity, but as a first approximation, it is okay. And we see that the presence of this parameter delta, it gives us a memory effect. The system becomes non-local in time. But qualitatively, the system can be easily understood. So dashed lines are without Schwinger effect, solid lines are with Schwinger effect. And you see that several orders of magnitude damping of the generated field. And also this dark curve shows the produced particles. Their energy density may be even larger than that of gauge field. And so we start reheating our universe still during inflation. Okay, and finally, we also tried to do some model independent constraints, because of course you can always take these equations and in the model you are interested in just to launch the program. But if there are some model independent constraints that do not force you to solve numerically differential equations, that is of course better. So any inflationary model, at least in some short time interval, can be characterized by almost constant Hubble parameter and almost constant this gauge field production parameter psi. Of course, there is complication connected to these memory effects, which are introduced by parameter delta, but let us now do not consider these memory effects. So black and purple curves, these are the constraints existing in literature. They were derived also in this article. So this uncertainty, so that was the uncertainty in which we could look for our energy density rho E, rho B, or E dot B for given psi and h. And you see, it is rather big uncertainty, several orders of magnitude, or 3 orders of magnitude. It depends. Yes, but now with our method, we reduce this uncertainty. This band is due to Hubble parameter. So these are different values of Hubble parameter. But if we took just one single value of Hubble parameter, we get just a line. So already we have improvement in this field. But as I said, this is still work in progress, because we have to better understand the Schwinger effect itself and also how to deal with this memory effect. And here I arrived to my conclusion. So as I said, axion inflation model has many phenomenological applications, from magnetogenesis to baryogenesis to different interesting imprints in cosmological, in perturbations. And it is worth studying, of course, and we need a tool which is as simple as possible, but on the other hand, it helps us to reach good accuracy. And of course, there are standard mode by mode. There is standard mode by mode approach, and you can use it iteratively, even in the case of Schwinger effect and the back reaction. You can use it iteratively, but it is very time-consuming procedure. And we propose a method which, in a single numerical run, allows us to get results to high accuracy. However, as I said, we still have to work on it in the case where the Schwinger effect is present. And this is all for now. Thank you very much. Thank you much for your attention. Stand with Ukraine and peace to all of us. Thank you.
Okay, thank you very much, Sasha. You are actually a bit ahead of time, but that's fantastic because we start a few minutes late. So we are now on schedule. Very good. So thank you very much. Okay, questions. I see Kohei has his hand up. Kohei, please go ahead.
Okay, so Sasha, thank you very much for your nice talk. So I have a question. You have meant to mention about the validity of the Schwinger effect. So the formula you used is the constant and homogeneous electromagnetic fields. So, but in the case of the magnetogenesis here, is the magnetic field is the correlation length is around the Hubble scale, and it's time dependent. So the validity of the usage can be questionable. So do you have any comments on that? So, and is it something you try to mention in the nonlinearity of electromagnetic fields?
So thank you very much. So as far as I understand, the question is that here in this, if we use this formula, our electric and magnetic field, they should be homogeneous. And actually, those magnetic fields that we produce during axial inflation, they have the correlation length which is comparable to the Hubble scale. Well, yes. So I would say that this is also important remark. But well, what else we can do? We should just use some kinetic theory just to from the first principles to consider this production. But I mean, this is a disaster. This is very complicated task just to solve numerically, because and after that we will have to somehow connect this result of the kinetic equation, for example, and our gradient expansion formalism. So I would say that then better to do this everything on the lattice. Yeah. So
then you can do that.
Yes. But I mean, I think that even with this approximation, we could give good initial conditions, because as far as I know, the lattice techniques, they are not very good during inflation because of very fast exponential expansion of the universe. But during reheating, Dani has a very nice code that can do that. So we can provide some more or less reasonable initial conditions for this code, and then maybe a few last efoldings of inflation, which are very important for magnetogenesis and reheating, they can be captured by this Cosmo-lattice code. That's what I can say.
Okay. Thank you very much.
Thank you.
Thank you. Okay, I have a question and a comment myself, but are there any further questions or comments by people in the audience? Okay, I see no other hands, then let me go ahead myself. So just one remark concerning this last point you were making, Sasha. Actually, it is possible to simulate also in the lattice axion inflation, the nonlinear stages, because this is why I was asking you if you had seen my talk yesterday, because that's precisely what I show. Okay. So we have extended. No worry. You will have time, and then we can discuss offline afterward. But just for you to know, we have extended the code now to be capable of simulating during inflation, and because it's very few if-falls during the nonlinearities, this depends, of course, on the choice of coupling strength, okay? But for our reasonable choices of close to the upper bound from analytics, we can simulate it in full detail, all in three-dimensional full detail, okay? And this is very interesting because we've been able to compare with your results, and actually we have a slightly different dynamics after the nonlinearities hit in, but we also demonstrate that if we remove the gradients, because you don't have gradients, you know, you have a spatial distribution in the infrared, or you are removing also electric field curl times gradient of phi. if we remove those, then we reproduce your results, you know. Yeah.
That's
so,
very nice.
yeah, it's very nice. So okay, we will have to discuss. In any case, sorry, this was just a remark concerning a previous point. Now, question: when in your technique, which is still very, very nice, honestly, when you compute the boundary terms, somehow you mentioned that you are using this dynamical cutoff, which you give an expression here. But the fact that you say that these are based on Whittaker functions makes me think, correct me if I'm wrong, that you are probably using the analytic solutions to the mode functions to differentiate infrared modes excited versus UV. And be careful with that, because once the system becomes nonlinear, the functional form of those mode functions is modified. Okay, this is what we demonstrate in the lattice. And those analytic solutions are not valid anymore. And of course, maybe missing a little bit the boundary between excited and not excited is irrelevant, because the infrared modes are so excited that not catching up the frontier is not relevant. But you may want to, I don't know if with your technique, do you have access to spectral quantities like the spectrum of gauge fields, or this is not possible? Yes?
Yeah, sure. We can get the spectrum in the following way. So we just solve this equation of gradient expansion. We get the background inflaton and the gauge field, and then solve the mode equation on this background.
Got you. And a posteriori step, So probably if you do that, you know there is distortion of the mode functions, and then you are gonna change a little bit what you call the boundaries. Certainly they are not gonna come from Whittaker functions anymore. You know, I don't know if this is relevant or not, but yeah, definitely there is that aspect. And okay, so that was the question.
Yeah, I can answer. Thank you very much for the question. So you are right that we are using this approximate solution, but we needed only, you know, the mode is inside the horizon and now it crosses, and we need only this small part of the solution when the mode is still oscillating, and then it crosses the horizon. We are not interested in further. Of course, at later time it will deviate from Whittaker functions, but at this small time interval, we still believe that it can be
pretty good. Okay.
Yeah, approximated like that. However, you are absolutely right that we should make sure. Yeah, we should make sure.
Could be. Okay, so now the remark to you is that because in your approximation, as well as in the iterative procedure of Valerie and collaborators, you are only doing the homogeneous inflaton sector. Well, it turns out that when you plug in the full back reaction, meaning you do locally EV, okay, not just expectation value, but locally, you restore gradients of the inflaton, and then we restore the curl between gradient of inflaton with electric field. It turns out that there is a slight differences in the psi parameter of order 10%, you know, but this manifests exponentially in the prediction. So eventually that's gonna impact, you know, the difference. Just to let you know. Of course, when I don't know if when it comes to swinger per production with effective current you are putting, once I put that in the lattice, I don't know if I will be able to improve, but maybe we can discuss about it at some point, you know, because hopefully numerically we can do something better other than just that analytical approximation, you know, and hopefully we should get eventually the whole picture. Okay,
thank you very much. It would be great.
Thank you, Sasha. Another question by Sebastian.
Yeah, let me ask a very basic question. So what is your physical expansion parameter? So like the ratio, it's like there should be some ratio of scales that is small and that allows you to approximate.
But I mean, we do not do any expansion. So this system is exact in a sense that you just introduce this set of variables, and then you have an infinite chain of equations.
Yeah, but like, why is the truncation good?
Because you see, each of these quantities, it is some spectral density, something like square modulus of the mode function times k to some power. And if this power is very large, then any form of this function, it is rather smooth. But any form of this function, it doesn't change the fact that the maximal contribution to this integral is around its upper boundary, because you multiply by a very big power of k. And that is why you just, okay, it is dominated by the upper boundary, use the theorem of average, and so you just put this outside the integral, putting here kh, compute this integral, and approximately get this. So we do not have any expansion parameters. This is like an observation that for large powers, this should work. And it really works, but only during inflation. If we go to reheating, then the behavior of these curves becomes unpredictable. However, during inflation, we see the convergence.
Right.
So this is like empirical way. We tried this truncation scheme and showed that it converges. Okay, then it works. Mm-hmm. But there was a question we asked ourselves: what is the parameter? How can we control this? And we do not understand how to do this. No small parameter here.
Yeah, well, like the other way around, can you quantify the error? Like when you truncate at finite n, is there any?
Yeah, of course. This is the error. So,
but it's an empirical error, right? So here it's like.
What do you mean empiric?
Like you go to higher n and then you see that it converges, and then.
No. This is a real error, because this plot is shown for the case where we can do this in alternative methods. So we can use this mode by mode. Where is it? Yeah, so this mode by mode, we can just solve for the mode function for all physically relevant modes to compute this integral. So this would give us the exact solution, and it is shown by a black curve here. And these color curves are the solutions of our system of equations. So these are two different, absolutely independent approaches, and we compare these approximate results to this exact one. And the error is 0.5%, so more or less okay.
All right.
Yeah, of course, we do not have this. So in principle, we have even in the presence of back reaction. So we can use, for example, the result of iterative procedure to compare. But we did in another way. We just, as I just explained to Dani, we computed these time dependencies and also of inflaton, and then solved mode equations on this background. And again, mode by mode approach. And here is the error. So this is this reference value, which we compared with, is not a true exact solution, because it is based on the approximate solution of our, but it is a consistency check. If we got some 100% error, then something is wrong. But it seems to be more or less consistent.
Okay, I think it's clear, Sasha. No worries.
Mm-hmm.
Okay,
yeah, thank you.
Guys,
thank you.
I see no more questions, and I think we need to pass to next speaker. So thank you, Sasha, very much.
Thank you very much.
Yeah, and then I believe, Maxim, if you are around, please, you can go sharing your screen.
Yes, I'm around. Thank you.
Okay.
I just try to find what to share.
Sure.
Okay. Okay, sorry, I have to come back. Do you see my talk?
We see the front cover now. Yes. Okay. So it is a pleasure to have Maxim Chernodub. He's gonna tell us about electroweak model aspects in a strong magnetic field. So please go ahead. The floor is yours.
Okay. First of all, I would like to thank organizers to invite me to give this talk. And I hope that next year we will meet each other in much more peaceful world in presence at some other, maybe in 2 years, because it's the biennial conference, as far as I understand. And I would like to say that my talk will be a little bit kind of similar to some kind of field theoretical defect in the cosmological world. So I heard many interesting talks about early universe, cosmology, and gravitation. And here I will not talk about cosmology, I will not talk about gravity, but I will speak about Electroweak model and strong magnetic fields. So that's only one thing which unites with other speakers, but I hope it will be interesting because the question will be about the presence of vacuum instabilities, very strong magnetic fields, which potentially may be useful for early universe as well. Okay, so the idea, okay, let me just move forward. So first of all, let me just very briefly mention the scales of magnetic field in particle astrophysics, and I will mention then what kind of fields I do consider. So first of all, for our reference scale, it's 1 Tesla. It's just something which you can find in real life, either in loudspeaker, in the coil of loudspeaker, or in nuclear magnetic resonance imaging. That's approximately 1 Tesla. Then for particle physics, for us, its next limit is, I don't speak about graphene or other condensed matter analogies, condensed matter relativistic field theories. I will talk about real fundamental field theories here. Next step is QED scale. We here have Schwinger limit with approximately 10 to 9 Tesla, which is basically electric electron mass squared. And this type of fields actually do exist in the universe, or at least they are suggested to be existing at the surface of magnetars. So there's highly magnetized stars of that order. And actually this already field is very interesting because vacuum acquires very interesting properties. One of them is just optical birefringence of this type. And another one is a vacuum can act as magnetic length, which are a little bit similar to gravitational length. So they start to distort images behind them due to magnetic field. Okay, in the core magnetars, we have much stronger magnetic fields, 10 to 14. And if we then jump to next level will be a QCD scale. That's the fields which are created there are approximately 10 to 16 Tesla, or basically mass of proton squared. And those fields do exist according to numerical simulations or Monte Carlo simulations. They should exist at high energy, high relativistic ion collisions at CERN or at RIC. They are very short, they're transient, so they act 1 yoctosecond, 10 to minus 24 seconds. However, they also have traces in observables, so they're also very interesting. And in this talk, I will be interested mostly about Electroweak scale. So that's next step. It's 10 to 20 Tesla, which basically given by W mass. So the field is W mass of W squared. And those fields presumably can be originated in early universe, in addition to high temperature, of course, they will have there some kind of plasma. However, I will not stop there. So you can put your favorite picture of your universe here. I made this part blank. I don't know what we'll see there. However, I would like potentially say that if such fields were emerging at some point in the universe, the consequences could be very interesting. Of course, temperature here enters and can also affect the whole picture. But here, for definiteness, I will work only at 0 temperature regime, which turns out to be also very interesting. Okay, so there were many theoretical works which predicted that the theory vacuum should change. So vacuum should experience some quantum field, quantum phase transition, which will reorganize its internal structure. So the work started by Niels and Oleksandr in many years ago. You see here years. Then by Scalazub, then by Amber and Oleksandr, and I will mention some of them in the course of my talk. So the change of vacuum structure in magnetic field, what does it mean? So at QCD scale, there was suggestion that if you apply strong magnetic field, then some particular composite states, Rho-Meson states, short-living states can condense, and due to the magnetic field induced condensation, the vacuum may become superconducting. And Electroweak scale, the objects which appear there is a similar transition, and objects which play their role is the W bosons, which are not composite, and the model is very well formulated, so one can make kind of more solid consequences, make one more solid steps to determine the vacuum structure. And those prediction basically based on the classical equations of motion, which says that if you apply too strong magnetic field, then the vacuum should experience phase transition. There will be some instability, and the W bosons will condense in particular state. So all considerations looked classical, quite easy, and basically indisputable because it was classical field theory. And so the aim of this talk is to check whether do we have this picture really at zero temperature. And just what we do, we just apply calculations based on first principles, so lattice gauge theory. And I will show that, in fact, the situation is a little bit more interesting than the classical standard picture. So let us first understand why the instability occurs. It's very easy, just consider a free particle. For example, we can consider charged scalar, spinor, or vector particles. Here I consider particles with geomagnetic ratio 2, which corresponds to Dirac fermions or to W bosons. And one can show that in scalar field theory, there is no instability. In a spinor case, there will be also instability. There will be no instability either. However, if you consider vector particles, then we will see that because the spin of the particle can reach 1 or plus minus 1. In that case, at particular value of magnetic field, the energy of just standing particle can become negative, or better to say, squared energy, relativistic squared energy will become negative, which signals instability. That instability occurs exactly when particle mass equals to 0. Oh, sorry, when magnetic field is equal to particle mass. So we do consider a situation when particle mass is on 0 to be able to apply to electroweak theory. For W bosons, here we don't consider any interactions, just suppose the W boson is a free particle with geomagnetic ratio 2, we'll get this relation. So lowest mass state will have this type of mass. Here the mass in the absence of magnetic field, and one can see that indeed at some particular value of the field, which is corresponds to W mass, the field will, the theory will experience some transition because there will be instability in the field. So mass become imaginary. Okay, and it was shown that this instability leads to condensation of W bosons, and that particular state, since W bosons are charged particles, electrically charged particles, they should obey instability, they should obey superconductivity. But superconductivity is a little bit strange because we know that usual Meissner effect kills superconductivity, but here the situation is different, that you apply magnetic field to nothing, basically to the vacuum, and you get superconductivity. So it should be very exotic type of superconductivity, which should be anisotropically conducting without Meissner effect and so on. So I will not talk about this in this talk. My aim is just to establish whether we have something like that based on the first principle calculations. Okay, so now let me first highlight the theoretical picture of electroweak theory in strong magnetic field. So the idea that our understanding that we have ordinary vacuum at low magnetic fields, then while the first critical magnetic field, which is exactly what I was talking about, this is corresponding to magnetic, corresponding to the mass of W boson. So when we cross this first magnetic field, then there should be some inhomogeneous phase predicted by Sobol and Ambiorn and Oleksandr. It should appear then. It should be superconducting. And then, in fact, if you apply a magnetic field further, if you increase it further, then there should be a second field, second critical field, which corresponds to the Higgs mass squared. And this magnetic field, at this particular magnetic field, the electroweak symmetry should be restored. And this magnetic phase, this kind of magnetically restored phase, has been discussed for a long time by Salam, by Linde, by Olis, and others. There are many papers here in the list. So our question is just, okay, let's try to check this picture, whether it works or not. So do we have 3 phases at non-zero magnetic field in electroweak theory? Electroweak theory, I mean just simplest Lagrangian without any quarks, which don't play here essential role. So, okay, quarks, I mean leptons, no leptons at all. So just consider only bosonic sector of the electroweak model, basically Weinberg-Salam part. That's all. Okay, and the results, the theoretical results, which were appeared in this paper, and of course there were also other results at say Bogomolny limit, but here we took real masses, looks like that. So if you look just average, consider mean field condensates, you just solve equations of motion, find instability, and try to see what are condensates, what is the nature of that symmetry broken phase. You will find that indeed at some critical field, which exactly corresponds to the critical field found by Bernoulli and others, the W boson will appear, the W boson condensate will appear, and it will rise it will rise differently depending on the mass of the Higgs. At physical mass, it will be just solid line. Okay, so we will have some kind of second order phase transition at the critical field BC. And at the same time, at the same point, the Higgs condensate, which is non-zero, should go down. So that's in agreement with the ideas of Salom and Linde and others. So in principle, we should see motion towards restoration of the electroweak symmetry. Indeed, the energy of ground state will come down. So just it's okay. So we sit in the most energetic state. And also the vacuum should become superconducting. That I will have no time to talk about that, but one can basically define an analog of the density of superconducting pairs in the system, which corresponds to the right-hand side of second London equation. Basically say that if you apply magnetic electric field to the system, then your electric current will start to ignite dissipationally with some ballistic flow. So we don't discuss this topic, but we will see that superconductivity really indeed increases as we apply magnetic field. And we have here a second order phase transition. That's the theoretical picture. And if you look to equations, how they look like. So here the magnetic field looks along z-axis. Here we consider x and y-axis. And here how the theory predicts us what should be the superconducting state, or this Ambien-Olesen or Skauzo-Ambien-Olesen state. That's like that. So we should have W boson condensate, charged W boson condensate, which is homogeneous because of presence of the vortices. It's similar to Abrikosov phase, but it's not actually equivalent to that because Abrikosov state is destroyed by magnetic field. When you apply a really high magnetic field here in this case, it's vice versa, it's induced. So we have hexagonal lattice made of vortices. W condensate vanishes in the center of each vortex. There is some topological winding there. And interestingly, that the Higgs condensate should, on the contrary, should be a little bit enhanced the condensate. So here this magnetic field is 1% bigger than electroweak transition, lowest transition magnetic field, critical field. So it's a little bit above this field here. And you will see that the condensate is decreased. So here the value of the condensate at absence of magnetic field. We see that the condensate, Higgs condensate decreased. However, there are some maxima which correspond to the positions of the vortices of this homogeneous structure. And then one can get also superfluid component, which is neutral Z component of the condensate, which has a little bit more complicated structure, which is vanishing inside and outside vortices, but non-zero in between. So it's kind of secondary transport effect, basically, in this case. Okay, so you'll see that this is our theoretical prediction for the structure of electroweak state at high magnetic field, a little bit bigger than critical magnetic field. And in fact, this theory looks even more beautiful. So if you look, I will briefly flash some transparency, how it should look like if you just consider X, again, XY cut, so magnetic field goes outward of the plane. Here the colors means just phases of Z condensate, also of W condensate and Z condensate. Z boson condensate, and you will see various cuts, which are depending, of course, on the gauge, and the endpoints, which are not dependent on the gauge, are just positions of the W vortices. And here there are also blue and on green points, which corresponds to positions of induced vortices, which appear, neutral vortices, which appear in superfluid Z state, Z boson state. So it's quite complicated structure. It's not just hexagonal lattice, but it's kind of one of the lattice, kind of double or triple hexagonal lattice of the neutral vortices superimposed on the charged vortices or charged condensate vortices. So the structure will be quite complicated, and one can show that different parts of the system would transmit either electricity, so it will be superconducting, or they will be superfluid. So they will have some superfluid currents or superconducting currents. So it's a very, very interesting system and quite complicated. And so again, so now the question, suppose that we have this inhomogeneous state, whether we do have there the condensates, which are predicted to be in this nice structure. Okay, so that's our next aim, just to check if we have this second phase, which is superconducting, whether it's really superconducting, whether we have condensates which are predicted by the theory. And next step, how to do that? Okay, we know that reality is just classical picture from quantum fluctuations, and quantum fluctuations can do anything. It can destroy reality or classical picture. So that's why we have really to, and it has also anomalies, of course. So in this case, we have also to study the system on the lattice. Here, I very briefly flash transparencies because there are specialists here, and just believe me, just lattice gate theory. So we discretize the system, put it on the lattice, consider a Wilson action, standard Wilson action for SU2 part of the standard, of the Young-Mills, of Wien-Marshall model, pardon, and put the thing on lattice, consider dynamical fields. We have only SU2 field and U1 field, non-compact U1 field, so we don't have abelian monopoles here. We can have some Nambu monopoles on other structures or sphalerons, but we don't have any abelian monopoles because they will destroy all pictures. So the abelian field or hyperabelian field is non-compact. That's an important point. And the action looks like this, just standard action. It has a few couplings here. So beta, the corresponding to so G prime, two gauge couplings, and two couplings in the potential, Higgs potential, and also external magnetic field, which we induced in this particular way. So there are many ways how we can induce it with a chemical potential or say with Lejeune transformation, but we applied this simplest way, and we checked actually others, and we checked that results are consistent with each other. So we used this just shift of the interaction term in the action with the of the gauge fields with the scalar field, so with the Higgs field. We consider boundary conditions, which are periodic magnetic field put along the directions, and we considered pretty large lattice. And I would like to say that this type of calculations were done by organizers and also speakers of this section of this workshop. They were done at three-dimensionally reduced model around electric crossover because it was interesting to see how the transition evolves with magnetic field. It was interesting for baryogenesis. So in our case, we consider zero temperature. That's why we consider four-dimensional lattice. Okay, and so the first thing which we should do, we should fix the physical point. I will skip this, but I just mentioned that we have physical parameters in the system, and we try to fix the physical point. For us, actually, it was biggest problem just to fix it, to find couplings which correspond to the constant physics line. By constant physics line, I mean that you vary some couplings where, say, mass Higgs, lattice Higgs of mass of Higgs is non-changing. So that's why you basically change your parameter space, and you move along the same ultraviolet cutoff of your lattice. So it's just technically interesting to get those points, and then interesting to see how you approach continuum limit and so on. So it's technical stuff. However, it's extremely difficult and boring, complicated stuff, which took us almost 1 year to do with our computing power. So we fixed the physical point with those couplings. And then we have to introduce magnetic field. Magnetic field here, situation is quite complicated because we need magnetic field actually is quantized on the lattice because we consider periodic boundary conditions. And periodic boundary conditions, we have some limits. So if you consider biggest flux over biggest possible Wilson loop or loop in your contour, then flux must be zero because basically different segments, parallel segments of your contour will cancel each other due to boundary conditions. So that's why there should be quantization. There should be this kind of limit on this kind of restriction on your magnetic field, and that's why magnetic field is quantized. So magnetic field here is quantized, and it's given by this value. And yeah, and one important point that I don't introduce actually magnetic field, but I introduce hypermagnetic field because, as I said, we expect that at some magnetic field, the theory should feel the restoration of should experience restoration of electroweak symmetry. But magnetic field is defined according to the direction of the Higgs field in isospace. Therefore, it's senseless to speak about magnetic field in the symmetry restored phase. Therefore, we introduced hypermagnetic field, and that was actually seen in our Lagrangian because we coupled it to the so-called, I would say, Y field in continuum language, so to U1 subgroup of unbroken group. Okay, so we introduce this field, and the interesting point here, and actually in the broken phase, those are related to each other through the couplings and through the Weinberg angle. There is no problem. However, here there is one problem that the magnetic field cannot be made arbitrarily small, because if you would like to get rid of lattice artifacts, you would like to make lattice as fine as possible. But when you make lattice as fine as possible, so this is lattice spacing, the distance between nearest points on the lattice, then the magnetic field becomes large. And here K is the quantization number. It's quantized in terms of 1, 2, 3, so it's an integer number which says how many fluxes or pairs of fluxes do you have in your vacuum. In this case, they will be double not double quantized, but quantized in terms of even numbers, number of fluxes. So 2, 4, and so on, 6, and so on. So we cannot make lattice too small, or lattice coupling, lattice size too small, lattice spacing too small, or we cannot make it too big, because so we should find some kind of agreement within the two. And in our case, we have chosen this type of resolution of magnetic field, which corresponds basically to 15% of the theoretically predicted critical field. So we consider it's more or less good. However, it's still, for good resolution, we still move further. Otherwise, one can increase lattice size, but it's really time consuming and computer consuming. Okay, so this is our results. So first of all, we would like to check this theory written in pink. So this is our dream. So we have ordinary phase, this inhomogeneous phase, which I call superconducting vacuum, and then symmetry restored phase. This is our result for normalized Higgs condensate, normalized at 0 value. So at this stage, we see that once we apply magnetic field, actually it's hypermagnetic field, once we apply hypermagnetic field, the Higgs condensate almost not changing, and then it starts to change a little bit, close at the phase transition, or the transition point, I would say, and goes down clearly without almost any errors, numerical errors, just goes down, and then finally gets to 0. So this is a normalized, Higgs condensate. So we clearly see that there are 3 phases here, with 2 different phase transitions, and those phase transitions are okay. The first phase transition is quite close to the theory, but still different. So it's 0.7 of prediction. So it says that quantum fluctuation should be quite large. That's why the classical answer should be corrected, but a little bit. So qualitatively we restore this, and the second transition appears actually pretty close to Higgs mass. So the answer should be 1 here, but we get 0.97 approximately. So we qualitatively, we do restore symmetry, we do restore theoretical prediction, so we do see it. So theory approximately works in qualitative level, but not on qualitative. And however, there is a difference that the theory predicts that the transition should be of the second order, as usually in many quasi semi-classical approximations. In our case, we think that we see actually crossovers, because if you look to Higgs susceptibility, you'll see this strange behavior. So you even don't see peaks, which would you expect to see at the transition. So it's something extremely smooth and probably analytic. So we do not see any thermodynamic discontinuity here, or some discontinuity in the derivative. So we do associate those transitions with crossovers. Unfortunately, we cannot make finite scale analysis because, as I said, the field is quantized. We cannot choose the magnetic field in between without really changing our lattice size. So yes, and we see really symmetry restored phase. So we get basically 3 predictions by the theory. They basically qualitatively they work. We see 2 phase transition with three phases, and we do see the symmetry restored phase. Okay, that's one thing. However, the question is right now what to say about intermediate phase. So what is intermediate phase? Okay, so we moved here at the point k equal to 9. Again, k is the number of pairs of vortices. So here there should be 18 elementary fluxes of hypermagnetic field, and it's pretty in the center of this diagram, basically in the middle. And here, how the vacuum looks like. So here are blue line denotes the equipotential, I would say, values of the W condensate, and the Higgs condensate, the same surfaces for the Higgs condensate are noted by green. And you see that we do really see some kind of vortices around. So there will be actually, one can count, the number corresponds to approximately 18. So there are those vortices around. However, those vortices, as you may see, they are not they're not forming the lattice. So they look like more just a little bit disordered. Then if you look to the structure closer, so this is a different configuration, for example, if you look closer, you will see that, yeah, so it does not look even straight, so they are vibrating a little bit. So this is just a 3-dimensional configuration, and lines here indicate the lines of magnetic field. So we do really see here some kind of not a lattice, but some quasi-classical structures which are predicted. However, they are not arranged as predicted by the theory. So probably so it's not okay exactly with the theory, and the role of quantum fluctuations probably is seen important. And the next step is just to see how those vortices look like. Here, I just make a sketch of two-dimensional plane. So we take the vortex, we take the configuration, some typical configuration without selecting it, exactly the same value in the same phase, and just cut it and look to various condensates and so on, without cooling, without any type of smoothing, without anything. Just look at the configurations, and that's what we see. So, for example, we see that okay, let's look to Z flux. We will see here some points which are exactly 18. Here in this case, we will see some points which correspond to vortices. Those vortices are clearly not in the hexagonal phase. However, they're more or less structured somehow. And if you look here to those regions which are made, with different colors, especially, they show you either two vortex kind of state or two closed vortices and three closed vortices. So they can usually identify them at different quantities at those different spaces. So here we have vortices, right? If you look to those vortices with D flux, here are maximum of Z flux which carried by those vortices. One can see that Higgs phase, Higgs field is enhanced at the cores of the vortices, which is in agreement with the theory. We expected that, as I have shown a few transparencies before. That's good. Next one, we will see that the W condensate, transverse W condensate, which corresponds to the spin elongated along the line of magnetic field. So our background magnetic field is along the third direction. So it's just out of the plane. So this state is made of transverse W fields, so WX and WY, and which corresponds, as says, it's perpendicular condensate. And so those condensates, those condensate pair parts should be subfields should be suppressed inside the vortex, and that's exactly what we see here. So as in the because of vortices, the superconducting condensates must be destroyed, and here we do see that. So inside the vortex, Higgs field is increased, and the W condensate, which is superconducting condensate, is depressed. That we clearly see here. Again, okay with the theory. However, there is an expected point that we can calculate the condensate not only along, of course, the perpendicular to magnetic field, but also along magnetic field. So that would corresponds to Z component of W condensate. And then we'll find surprise that actually those three components are of the same order, which is totally off the theory. Theory doesn't predict that. Moreover, it forbids that, because this component corresponds to the zero projection of the spin onto magnetic field axis, and this one should be actually heavy, so it shouldn't condense. However, we show that the symmetry in W condensate, we see that the symmetry is extremely small, of the order of 10%. So that's something which is not okay with the theory at all. So those vortices are a little bit different. And then we see anti-screening effect predicted also by the theory, which looks okay, more or less, despite smallness. So we see that the vortex structure induces some hypermagnetic field, which correlates with the position of vortices. And also, probably okay, as I said, we see also ZX and ZY condensates, so neutral type condensates. We see them, but as I said, in the theory, they are quite wild, so they are quite specific, and they are not actually easily identifiable because they change wildly. So we do see, but we see some fluctuations of the Z condensates, semi-classical type fluctuations. And that means that we also restore theory. And on the contrary, here, the Z component of Z field is 0, which also agrees with the theory. So, okay. So we see general agreement with the theory apart from the lattice structure. So lattice structure is not hexagonal. And also there is a strange effect that we get some longitudinal component of W condensate, which shouldn't be there at all. But it's robust, that would really we see that. So now you can ask, okay, but how things develop in Monte Carlo time or in time, but we don't have time, we have Monte Carlo time. By the way, how much time do I have? I have not noticed that, how we started.
Well, you will make 30 minutes since you started in 2 minutes.
Okay, so I have kind of 2 minutes left, right?
Yeah, plus another 5 if you want to extend, but
okay.
then at the expenses of the question time.
Okay, so now I come back to Euclidean time. So here is the following thing. So we just take to visualize how widely fields are fluctuating, one should make movie. And so this movie is made of the following. So we just take the theory, we just take configuration, generated it, and then started to update it in Monte Carlo time, just looking how it evolves, and then see how it changes in Monte Carlo time. Equivalently, you'll get the same picture. You can just take your configuration, make say, time slice somewhere or kind of slice, and then move along the configuration, this one configuration along, just visualizing slice by slice and making some smoothing so that your eyes does not get tired quickly. So that's what happens here. So here we consider the fluctuations of the Higgs field in the broken phase. We stay at zero magnetic field, and here it is. So this is just pretty fluctuating medium without no structures at all. Then we move to the exactly to that phase, which is in between the two transitions, which we call superconducting phase. And here you see the Higgs field is already quite big. We have quite big fluctuations. Moreover, I would like to mention, and actually they are put in the same scale. So all of them are put in the same scale. So here quantum fluctuations are quite small, and here we see quite big, large classical fluctuations. And I would like to say that lattice people would immediately say, oh yeah, you made some smearing, smoothing, or some other RG scaling and so on. No, here no RG flow. So here is just original configuration. So we take it without any specific preparation, and that's what we see. We see that those vortices, so we clearly see positions of vortices, which are maxima, they are moving. They're moving like in the fluid or in the gas, basically. So they're moving around. So this fluctuation, this situation, this configuration is lively. It looks like a lively fluid type of or liquid type of state. And however, we see large quasi-classical fluctuations. So it's not, again, it's not hexagonal picture. However, okay, there are some motions of those objects here in the vacuum. Again, let me say that it's zero temperature. There are no chemical potentials. So this is really pure vacuum state. So we have, that's what you see, it's just really vacuum. However, a high magnetic field. And then let's increase magnetic field and come to the phase where we have restored symmetry. And here you see again the fluctuations become a little bit different than we saw before. However, as you see, they are very small again at the same scale. So we do really have small fluctuations, and we do really have restoration of the symmetry. So nothing interesting is here. And you can do the same with the W fields. So they're pretty the same. So just it's no magnetic field, then you come to the middle. Here one can say that W's fluctuate more. So you have just semi-classical configurations, which are vortices, plus on top of them more fluctuations, quantum fluctuations, but still vortices are easily recognizable. They merge and they're going outside so from each other. So there is some life here, and it's again reminds a kind of fluid. Again, if you move to large magnetic field, we get this type of configuration. And then you say, okay, but why it is so? Why that happened, and why the quantum fluctuations are so important? Of course, we cannot answer that because it's, I mean, right now we just did first principle simulation, but we ask ourselves, okay, but imagine that we just a little bit change parameters. So we liked very much to talk about semi-local limit, where basically SU2 group of U1 of SU2 cross U1 electroweak group is decoupled basically. So then you basically get a two-component scalar field which interacts with the U1 gauge field, so semi-local limit. And then we said, okay, let's go to semi-local limit. Let's look what happens. So we took some unrealistically large lattice, one of lattice couplings, and we saw that, we get the hexagonal lattice. We were really impressed that we really got the hexagonal lattice, and we understood that when we put beta, so this lattice W coupling is a coupling which in front of non-abelian gauge fields large, then we suppressed basically non-abelian fluctuations. I mean fluctuations of W's and Z's. When we suppress those fluctuations, we get perfect lattice which are predicted by the theory. So it's really hexagonal one, and the fluctuations of it, okay, they exist, but they are pretty, like I would say, like in crystal. So we see some phonon modes, Euclidean phonon modes which are moving around, and that's all. So it's extremely important what kind of Weinberg angle we have. So with our present Weinberg angle, we don't have a classical picture to work. Okay, it works, but it works in this quantum way. So instead of we have vortices, nice vortices which are qualitatively more or less apart from this W, one of the component of W's. They're very well described by the theory. However, they form not the coherent crystalline structure. Probably we have a fluid there. However, if we would increase Weinberg angle and go to semi-local limit, then we would get actually nice theoretical solution with a very nice abricos of lattice. So no problem at all. So values of couplings are important. Okay, that's our picture. So in theory, we should have something like that. In reality, we get something like this.
Maxim, yeah. Sorry to interrupt you. Just to let you know, you've been 34 minutes speaking. So in 1 minute, you should be wrapping up.
Yes, that's conclusion. Exactly.
Thank you.
Exactly. So just let me briefly flash this transparency. So we found for the first time the phase structure of zero temperature electroweak theory from the first mental simulations. We do found three phases. So the three-phase structure, so ordinary phase, then homogeneous phase, and symmetry restored phase is predicted. We see some quantitative and sometimes qualitative difference from the theory. We do really see no lattice structure there. However, we see vortices which are similar to the theory in many respects. And we expect that the similar structures may in principle exist in QCD because we had some work some years ago when we did unquenched QCD, quantum thermodynamics at lower magnetic fields, much lower magnetic fields. We did experiment and we see numerical experiment and we see similar structures which form fluid, which are actually much more difficult to observe because of the composite state of constituents. Okay, thank you very much. I finished. Thank you.
Thank you very much. Okay, thanks a lot for the talk. Are there questions from the audience? Yeah, I guess Stamasios is applauding, but also asking a question. So please go ahead.
Hear me? Hello?
Hi.
Hi. I was just wondering whether, since you mentioned that there is this region of parameters where you have this W condensate that isn't in agreement with the theoretical expectation, you had a film of that, a video of that, that would show what was going on.
You mean of this one?
Yes, of the asymmetry in the W condensate. What does it mean that it's not okay with theory in more tangible detail?
Because this component should correspond to the projection 0 of the spin of the W. Mm-hmm. And this component should not condense. Because if you look just to a very primitive example at the very beginning, just if you look here, then this when S is equal to 0, then the effective mass of a vector field just rises with magnetic field. Or sorry, just no, F is 0. Yes, in this case, it should rise with magnetic field, right? So it's just should not. Basically, we shouldn't have anything interesting here. So it's not something which would be kind of this field should not condense. But we do see this field. We see that it's large, and it means that it condenses. At least it's semi-classically large. So
Maxim, can it not be? I mean, in any non-abelian gauge theory, there's going to be nonlinear interaction between the gauge bosons, and since you have instability in the other ones, can it not be a dragging effect from the nonlinear interaction among them? Because at the classical simulations, I would expect that for sure, you know, even if they don't have the instability in first place, you know.
Yeah, that's exactly what you said, Daniel, but that happens with Z boson. So there is dragging effect. So W boson drags Z boson. And so superconducting condensate makes superfluid, but they are the dragging appears between the equals, you know, so this one is transverse and this one also transverse. There is no longitudinal component. That's a problem. So we don't know why
it's the longitudinal of the W that seems to condense even though it does, even though it shouldn't. That is the statement.
Yes, that's the statement. That's the statement. Don't understand why. That's why we even originally we thought that we do not see because of Ambiron-Oleksandr strings at all. So we see something different. But right now we saw that we see them with some additional part because we have many arguments for and one against. So it's like.
I was just wondering whether the longitudinal component could fluctuate, but it may fluctuate at a scale that is much, much smaller than, and therefore one would think that it has condensed, even though in reality it does not. It does not condense.
No, we exclude the situation. There, basically, if I would plot this picture against, say, longitudinal picture, they would be pretty the same. You would say that they're almost identical. So that's why the condensates appear at the same position. We see no error in our program. So that's
whether some correlation function would show that they do have a decay of correlations, even though they are in the condensate.
Yeah, probably, but that's maybe for the future study. Yes.
Okay.
Thank you.
I have a question myself, but is there any other question from people in the audience? I don't see more hands raised up. So let me ask you, Maxim, can you think, or is there any clear application of this effect in the early universe that we could think we've made electroweak plasma of particles, but we have such like a great magnetic field, which was generated maybe, say, from the scenario that Chiara Sobol was presenting you before. Is it conceivable to think about magnetic field sufficiently strong that would trigger this effect in the early universe to produce this condensation?
Okay, so the question is very good because in fact here I considered everything at zero temperature, and of course the universe is probably not so much zero. But imagine that at some point that's about this picture, yeah, right? So what we have here at early universe, so whether we have this big fields there or not, but imagine that some of those fields survive by any reason, and they form some kind of knots. People call them Chandra-Sikal candle states or Taylor states or spheromax, depending on which field you are from. So they form knots, and those knots can survive for a long time. I'm not talking about corona of sun, for example, where you have those long-living knotted structures, but just this one. So you will have some knot, which will have a magnetic field, which is produced by, which makes this part of vacuum superconducting, and this part superconducting vacuum will support current, which will produce the same magnetic field. So it will be self-consistent solution with magnetic knot. It's some kind of egg of magnetic field which moves around and self-supporting. So in principle, that's possible, like that. So, but that's of course pure speculation at that point. But I'm very happy that we do see really those phases, and we see that it looks like they are superconducting, because we cannot check superconductivity in this Euclidean approach, but we do see that there are semi-classically large condensates which are homogeneous as predicted by the theory. So that could be interesting, probably.
The reason why I ask actually is because if one could think of engineering a setup in the early universe like that, this kind of instabilities that produces this condensation, I'm pretty sure it would produce a large amount of gravitational waves, because these are probably exponential instabilities. And then, whatever gravitational wave background you could produce out of these instabilities, it would inherit spectroscopic properties due to the scales corresponding to the inhomogeneities of these condensates. You see?
Oh, that's interesting. Right. Because we do see instabilities. We do see that instabilities do occur. So that's our result. Yes, but they're kind of smooth. You see, they're unfortunately in the same way as in electroweak theory, electroweak model, electroweak thermal transition is crossover. Here we also see crossovers.
Okay.
But we see them. Yes, indeed, we see some instability.
Okay. Well, thank you.
Thank you.
If there are no more questions, then we can thank Maxim again. Thank you very much. And then we can move on. Let me check who is next. I think next is Chiara Caprini. Chiara, hello, are you there around?
Hello.
Hi, Chiara. All right, you can share a screen. I'm gonna lower my hand here. Yeah. Okay, excellent. Okay, so it is a pleasure to have Chiara Caprini. She's a leading scientist in computing gravitational wave backgrounds from the early universe, and she's gonna tell us about aspects of these backgrounds for the will be first space-based mission for gravitational wave detection, LISA. Okay, so please, Chiara, go ahead. The floor is yours.
Thank you, Danny, and thank you very much to the organizers for this invitation. Yes, I will try to give you some overview of possible sources from the early universe that possibly provide signals visible in LISA. And in the last part of the talk, I will focus on more recent results that we have been obtaining. So, well, first of all, in a very general way, what is the object of my interest is, to use gravitational waves actually as a cosmological observable, and how do indeed gravitational waves help us to probe cosmology. There are two aspects, so we can use them to probe the late time universe, and so the energy content of the late time universe. But we can also use them to probe the very early universe, and this is what I'm going to tackle in this in this talk with a particular then focus on signals that can be visible at LISA. So what is the main message? I think, I mean, you already had you know, some talks about it in this conference, so I'm sure all of you are aware of, but let me just repeat it for clarity. So the point is, if you imagine that you have on this axis the time in the early universe, or growing time and decreasing energy, of course we know a lot about what has happened from the CMB at recombination, from Big Bang nucleosynthesis at the MeV scale, from CMB anisotropies. They tell us about inflation, but there can be, depending on the energy scale of inflation, a wide range of scales between inflation and Big Bang nucleosynthesis, on which we cannot have a direct access with photons because they are tightly coupled. And there maybe it is the, you know, where we can get some help with the gravitational waves, because there are interesting processes that might have happened at these energy scales. For sure, we had two-phase transitions also within the standard model. Beyond the standard model, we can have obviously, you know, all kind of phenomena like baryogenesis, dark matter candidate. We will have reheating after inflation. So gravitational waves are unobservable that potentially grants us access to this kind of phenomena. So that is the main interest. Now, LISA, as we will see, is you know, even though it was not planned or it was not somehow formulated as a cosmological probe at all. It does have some interesting properties in this respect of probing gravitational waves from the early universe, and we will see especially why. But let me first tell you a couple of notions about LISA. So it is the future gravitational wave detector in space. Provisional launch date is the 2035. It is now very well advanced into the ESA mission schedule. Obviously, the advantage of building an interferometer in space is that there is no seismic noise, and one can have much longer arms than the interferometers on Earth, and longer arms means lower frequencies, sensitivity to lower frequencies, and sensitivity to lower frequencies means another complete different set of sources that can be accessed. Right, so LISA is going to be this triangular configuration, and now the arm length is settled to 2.5 million kilometers, and it will be on a heliocentric orbit following the Earth. Now, LISA, as much as you have seen with LIGO Virgo, measures the gravitational wave signal from in spiral, merger, and ring down of compact binaries. In particular, the merger and ring down of massive black hole binaries. This is why it has been conceived to access these very massive black hole binaries that are in the center of galaxies, but it can also measure the spiral phase of stellar origin black hole binaries and also binaries in the galaxies. So it does have, you know, access to different kinds of compact binaries, obviously signals emitted in the late universe, so astrophysical sources, but it will also, at least in principle, might have access to a stochastic background. Now, stochastic background is what we are after if we consider early universe sources, right? So there are actually sort of two categories of stochastic backgrounds. First of all, what it is given by the position of sources that cannot be resolved individually. And so in the time series of the gravitational wave strain, it just looks as noise. This may come either from, again, compact binaries that are too numerous and with too low signal to noise ratio to be individually resolved. And so this is going to be the astrophysical background. But it can also be produced by signals from the early universe because, as we will see, they are in general characterized by a very small correlation scales, typically the horizon at the time of the production, and these are very small with respect to the detector resolution. That's why this particular early universe signal, they appear as background. And so the quantity we are after under an hypothesis of statistical homogeneity, isotropy, and Gaussianity of the source, and consequently also of the tensor mode, the quantity we are after is the energy density power spectrum. Okay, so we believe that more or less, if you know this quantity, at least it gives you a first access to the signal, if not exhaustive. Now, the problem is that stochastic gravitational wave backgrounds are extremely difficult to extract among gravitational wave signals. Why? Because they look like noise, obviously. So here we have the strain as a function of frequency. Today, you see the sensitivity of the LISA interferometer, and you see a big bunch of sources, massive black hole binaries, galactic binaries, stellar origin black hole binaries. This is a confusion, so foreground or astrophysical background, as you want to call it, from the galactic binaries. And here you see there is this little bump, which might be a signal from the early universe. So you really need to be able to go dig this out in a global feed procedure of all the signals that you see at much higher signal to noise ratio. So this is a caveat that it's important to clarify. It is a difficult search. Okay, so just a few definitions, because I'm sure you are very much used to the generation of gravitational waves or the tensor mode from inflation. And I just want to emphasize, as we will see, this is not something which is really very much interesting for direct gravitational wave detectors, because you know, with the present bounds on the energy scale of inflation, it is very small. So what do we want? Well, we want this part, right? So this is the perturbation of the energy momentum tensor that couples to the tensor mode, and actually in the evolution equation for the tensor mode is what appears like an active source. Tensor anisotropic stresses, and this actually can act as gravitational wave sources at any time in the universe. We don't need to be during inflation to have this kind of active gravitational wave source. So we can have signals from other kind of processes arising during the radiation dominated era, for example. Now, as you can appreciate, then now this active gravitational wave source is a causal source, and so it needs to respect, obviously, causality, which means that if we call, like with this quantity L star, the characteristic length or time scale of the source, so basically the typical size or time of the tensor anisotropic stresses, well, this needs to be bound by the Hubble scale at the moment of generation of the signal. And therefore, this can translate in a kind of characteristic frequency of the gravitational wave signal coming from a source operating at a given time, that here I call T star in the early universe. And then I can redshift this frequency to today. And then basically just rewriting the Hubble factor, it is possible to put in one-to-one correspondence modulo this quantity here, this parameter here, the frequency today of the gravitational wave signal with the energy scale in the early universe where the source is occurring. And so using this relation, it is possible to build this kind of plot in which here there is the frequency today of the gravitational wave signal, or let's say the characteristic frequency in the gravitational wave spectrum of the stochastic background. Here there is the energy scale in the universe of the source, and obviously gravitational wave observatories have their sensitivity range of frequencies. And through this particular relation, one can then see to which energy scale or they would be sensitive, you know, if there were gravitational wave sources at this particular energy scale, then this particular gravitational wave observatory might pick them up. And clearly you see, that these open up, as I was saying, energy scales that are characteristically much higher than our usual cosmological probes like Big Bang nucleosynthesis, large-scale structure, the CMB, etc. So we really access you know, the regime of whatever, 10 to the 5, 10 to the 10 GeV, etc., depending on the observatory. Now here, obviously, I fixed this value to 1, okay, because this is an open parameter. And so just, you know, to give you two known energy scales, so the QCD energy scale with some reasonable assumption for this parameter falls into more or less the nanohertz frequency range, which is accessible with pulsar timing arrays, while the Electroweak scale with this other assumption for the parameter, we will see more about this in the rest of the talk, corresponds to the millihertz, which is the frequency of sensitivity of LISA. So you see that there is potential there because we might access interesting energy scales in the early universe by operating in the case of pulsar timing arrays or future gravitational wave observatories. Now, this is all very nice and very beautiful, but I only told you about the frequency. Now, the other point is the amplitude, clearly, because all these observatories, they have a minimal sensitivity, right? And so if the source is, the signal is too low, we won't be able to pick it up. So here you see here the gravitational wave spectrum as a function of frequency today, together with the sensitivity of a few interferometers. So we have pulsar timing arrays, we have space-based interferometers, we have Earth-based interferometers, and we have obviously the CMB through B modes. So this is not a direct gravitational wave detection, but it still is. And so the game now is to try to populate this figure with signals that are visible. So overcome the minimal sensitivity of these devices. So I will give some in this context, a few examples. Some of them are a bit outdated. Please bear with me. You know, in order to focus on really on LISA. So the first thing, so let's consider a few cases from inflation. So operating during inflation. So here, what you want to do is to translate the usual tensor spectrum. You are used to see it in this way into this quantity omega. It is done very easily through a transfer function, and you see that clearly the relevant quantities here are two. One is the tensor spectral index, and the other one is a tensor to scalar ratio. And unfortunately, these are, you know, in the context of vanilla slow roll inflation, both the fact that the spectrum is red or reddish, let's say, and the energy scale is bound, makes this signal out of reach. Okay, clearly we can have in general some form of preheating, like you have seen very interestingly, but this is in general, you know, without much assumptions at much higher frequencies than what is accessible here by these interferometers. So the game during inflation is to enhance the slope while respecting the bounds of the CMB. And this can be done in many different ways, but in general, what you want now is that if before you had, you know, generation out of vacuum, you want to insert some active source that always in the context of slow roll inflation changes what the dynamics at very small scales. So one example you have seen also in the previous talk, the first talk of the afternoon is, you know, for example, this kind of coupling. Now this figure is largely outdated, so, but just to tell you that in this case, you might obtain, it is not clear nowadays whether to a level which is visible, but you can obtain an enhancement of the signal at high frequencies. Another possibility, which I find very interesting in the context of LISA, is through second order scalar perturbations. In general, these are guaranteed signals, but at lower frequencies. In order to have them also at higher frequencies, you need to do some fine tuning, but it is interesting, as pointed out by these people, because you know, there is still a window in the mass of possible primordial black holes for which there is no constraint. And so they can constitute the entirety of the dark matter. And if you suppose that you have a generation mechanism during inflation that provides you with primordial black holes of this kind of very small masses, then this leaves a signal, a very high signal to noise ratio signal in LISA. So this is an interesting possibility for LISA. Now, quickly, another possibility is to have gravitational signal from cosmic strings. Okay, so in this case, one would advocate that there is some high energy phase transition. I think we will hear more about it after the coffee break by Valerie. So here I'm presenting, you know, basically in this context, the gravitational signal can be there or cannot be there. It is extremely model dependent what is going on, but in the, you know, in the context of if you believe in the Nambu-Goto local string approximation, then you can have signals that are very much visible by LISA, and you can have interesting constraint on the string tension, and also the possibility of, you know, here I don't know why they didn't put LIGO Virgo, but you know, the possibility of having multiple detections in different observatories. Okay, and now let me come to my favorite topic, which is gravitational signal from first order phase transitions. Okay, so this is also you know, something that might in principle happen in the early universe, as we have also been seeing in this conference. So there the idea would be that you have for example the X or some kind of order parameter that performs a first order phase transition. And then you have several, if so, you have several possibilities to generate your gravitational wave source, be it quantum tunneling, thermal tunneling, it doesn't matter, because as soon as you generate bubbles, then you do have already just by the bubble wall themselves a generation of tensor anisotropic stress by the scalar field gradients at the bubble wall. But in general, in the early universe, you assume this is happening in a thermal state. So there are particles all here around, which are coupled to the field. And therefore, this bubble, when this bubble expand and collide, they set the field in, they set the fluid around them into motion. And so this bulk fluid motion also generates a gravitational wave signal. They can be in the form of, compressional modes, sound waves, or they can also be in the form of vortical modes, like turbulence. And in general, you can have, if there is turbulence, you can have electromagnetic fields present as well, because if you have a tiny seed field, then turbulence will amplify it. And so then the electromagnetic field also has on its own, it is a source of tensor anisotropic stress. So there are many possibilities, you see, at the first order phase transition to generate gravitational waves. So in particular, let me tell you a few words about these two sources that we have been recently reanalyzing with some of my collaborators. So we have thought about generation of gravitational waves from magnetohydrodynamic turbulence after a first order phase transition. So basically what is this is a phase of chaotic fluid motions that arises if you are in a condition in which the Reynolds number is very large. So the advection term in the Navier-Stokes equation is larger than the diffusion one. And then if you put some reasonable values for these parameters that you see here, kinetic viscosity, root mean square velocity or kinetic energy in your bulk motion, typical scale, this would be the L star parameter I was telling you before, then you see that the Reynolds numbers is typically huge in the early universe, so you expect to have both kinetic and magnetic hydrodynamic turbulence. Now, this system is complicated because you have the scalar field, which is driving the transition. You have the surrounding fluid, to which the field is coupled, which is set into motion by the bubbles, and then you have the magnetic field. And this system can be highly nonlinear, especially if the first order, especially if the phase transition is strongly first order, and therefore it needs to be tackled through simulations. And this is what we have been doing using the two codes that are available out there to simulate this kind of problem. One is the Scots code developed by the Helsinki group, and another one, the Pencil code developed by the Nordita group. These two codes are very much complementary. And so we have used them both to try so they both output the gravitational spectrum. So we have used them both to try to predict the gravitational signal from magnetohydrodynamic turbulence. Now, unfortunately, it is very challenging to observe the onset of turbulence in simulations because, in general, it's computationally challenging because in general, if your phase transition is not very strong, the nonlinearities arises on a time scale which is much larger than the time of the simulation. And so when you are in this condition, you don't see turbulence, you see the occurrence of sound waves, which is also a very important source of gravitational waves. But there are some hints that in simulation reaching the mildly nonlinear regime, you have the generation of vorticity and therefore turbulence. So it is something which is in general expected. So what we have been doing is that we constructed an analytical or semi-analytical model of non-relativistic MHD turbulence and the source. We have validated this model with the MHD simulation using both codes because we weren't able to see the onset of turbulence from the simulation itself. We have put a turbulence spectra in the initial condition to start with. So this is the big caveat of our analysis. And then what we have done is that we have calculated the gravitational wave signal from the simulations, from our semi-analytical or numerical integration of our semi-analytical model of the source, and then with a very basic analytical assumption, which I don't have time to explain here, but which is actually pretty interesting from the point of view, let's say, of the analytical understanding of what is going on. And this third way to tackle the problem has allowed us to provide an analytical template for the gravitational wave spectrum that you can use in your favorite phase transition model if you want to see what is going to be the gravitational wave signal from MHD turbulence. Okay, and so here are some advertisement plots. Right here you see the gravitational wave spectrum today as a function of wave number, normalized wave number. Now the psi would be the L, this L, the typical scale of the source, and for different values of the kinetic energy. Now this is input parameter because we input in this case the hydrodynamic turbulence into the simulation to start with, and here you see the results from simulations. The result, the black line, is the result from the semi-analytical, the numerical integration of the semi-analytical model. The gray line is the analytical model. And so you see that they pretty much overlap. This is, with the Scott's code, we have the same thing with the pencil code. So in the case of MHD turbulence, in this case, the code has the expansion of the universe folded in, and therefore we can actually chase also the small scale behavior, and we have found that there is a break in the spectrum at the characteristic time scale of the source. And here as well, the result of the simulation, and the dot dashed is our analytical formula, and so we have a pretty good prediction of what could be the gravitational wave signal, which is ready to be used, really, in dependence of the parameters of the input parameters of the phase transition. And now let me close with some example of signals using this result. Okay, so first of all, so I've been mentioning before, the fact that the scale of the electric symmetry breaking is actually corresponds to the sensitivity range of LISA. So this is really something which, to my mind, makes the LISA observatory very, very promising, because it offers an interesting connection with beyond the standard model physics. Of course, one needs to have a first order electroweak phase transition, which so one needs to go beyond the standard model to have that. But then, this offers the opportunity to have nice multiple probes of, for example, binary asymmetry or the presence of dark matter candidates. So it is all very nice, and there are models, some of them might be constrained by now, but there are models which were out there before, actually evaluating their gravitational wave production. So here I want to just to flash the result. So this is the LISA sensitivity, and this is the gravitational wave energy density as a function of frequency today. And here you have,
Chiara,
yes?
sorry, just 1 second, just to let you know, you've been speaking for 30 minutes, so you have 10 minutes now, including questions, okay? Yes.
I will speed up. Yeah.
Okay.
So just, in this particular scenario, for example, we took just one possible benchmark point, and which would lead to a visible signal in LISA. And at last, so I want also to advertise this PT plot tool that we developed in the context of the LISA cosmology working group, which allows you to, plot the signal or analyze the visibility of some signal for your favorite first order phase transition model. Here there is no turbulence, but there is the sound waves. And at last, let me flash this. So if we are able to or ready to accept that maybe even the order of the QCD phase transition can be altered, by the condition of the early universe, then, as I was saying before, basically what the observatory that corresponds to the QCD energy scale in the early universe is pulsar timing arrays. Pulsar timing arrays observatories have recently measured some common noise excess. Okay, so I just want here to flash the fact that we have analyzed this problem and we have seen that this, if one is ready to advocate that this common noise is actually a gravitational signal, then it would be compatible with gravitational waves generated by fully developed MHD turbulence. And this is the plot that we have in the paper. So these are the shaded area are the sort of detection, let's say, or what the would-be detection of different pulsar timing arrays observatories, and these are, boundaries within which the signal would look like, within which the signal would be compatible. And what I want to stress is that we do expect in this kind of model, this break I was telling you before in the spectrum, and this would occur at a scale corresponding to the horizon at the QCD scale. So in principle, we would have with PTA some access to, this particular scale in the early universe. And if you advocate that this kind of signal is due to MHD turbulence, so there is a magnetic field obviously associated, and this magnetic field then hangs in there and evolves during the radiation era, and then you can use it for, it would have the right amplitude to use it for other phenomenological signatures like, CMB spectrum, SID, the field in matter structure, and be constrained by future gamma ray telescopes. Okay, so this is my summary, and let me just maybe stress what are in my opinion, some open problems. So, so I told you, so in the context of LISA, what might be interesting sources of gravitational waves. And if one focus on this particular aspect of the capability of LISA to probe the electroweak symmetry breaking, and if one is ready to assume that this is in the form of a first order phase transition, then in general MHD turbulence is something that we do expect. Clearly we have a problem with the initial conditions because we can only tackle this system with numerical simulations, and in these numerical simulations we need to be able to simulate the onset of the turbulence, which is not done yet. Okay, so it is really I think this open question of how, if there are sound waves, how they are turned into turbulence, or how does turbulence arise. And then also the other point, which is very important, is okay, how do we chase after these kind of signals? And what we need from theorists is obviously a very accurate prediction of the spectral shapes, if we stick to the 2-point function, okay, as a first ballpark to detect the signal, and also improving data analysis techniques, of course, to extract this particular signal from the noises. Okay, thank you.
Thank you, Chiara. Thank you very much. Okay, are there questions? I see a couple of hands up, so let me start by Laura. Please go ahead.
Thanks a lot for the talk. It was super interesting. So you've shown an example of a signal that is within reach for LISA, where we can see both the component from the sound wave and from the turbulence. I was wondering whether there are there is some expectation of how these two different signals look like, whether one is peaked at higher frequency, expected to be peaked at higher frequency with respect to the other, or like larger or smaller amplitude, this sort of thing. And the second question is this parameter L star H star. I've seen during the talk that sometimes it's 0.1 or 0.01, and I was wondering, what is the idea? How do you fix that, and whether there is how do you choose those values? Let's say, yeah. Thanks.
Okay, so let me answer maybe first the second question, which is very important. So basically, what it is, this L star, more or less is the size of the bubbles at collision. So then, therefore, you can relate it. In general, it is related to the duration of the phase transition. If you assume that you know the velocity of the bubble wall, it is related to the duration of the phase transition, which itself comes from the axion. So in principle, if you are within a very well described model, from the axion, you can calculate everything. Now, the duration of the phase transition is just the time derivative of the axion, so this is easy. The biggest problem here to calculate is always the bubble wall velocity. This is very difficult because you need to account for all the interactions of the field with the particles surrounding it. And therefore, you expect, in any case here, to get something visible, the bubble wall velocity must be reasonably close to the speed of light. And therefore, I mean, in general, this parameter L, which is the size, is pretty much close to the duration, modulo some factor, which might be of the order of 0.1, 0.01, depending, so which is the bubble speed. Okay, so that's why you have seen it sort of fluctuating during the talk, because it is really something that in general we, when we do this, so my work is not really to, on the side of the phase transition modeling, it is more on the side of the signal, and for this, in general, we put it as an input parameter. Now, having said that, to the second question, so here the point is, this is largely unknown. So what we know is the shape of these two signals. We know that the peak frequency then, as I told you, corresponds to, in general, to the energy injection scale, which is going to be connected with the bubble size when they collide. What is the relative amplitude of these two signals is largely unknown now. And here, to do this particular plot, I choose a value which is random. Okay, I decided and I put it to 0.25. So there is one quarter of this kinetic energy in the compressional mode, which is turned into turbulence mode, but out of the blue. So this is, what I have been stressing, this is the direction in which we should investigate now.
Okay, thank you.
Thanks a lot.
Kohei, please go ahead.
Hi, Chiara, thanks for the nice talk. So I have one question on MHD. As far as I understand, your analytical estimate is based on the assumption that the equipartition between the velocity field and the magnetic field is established. And
no.
Oh, not really?
No. We needn't. So in general, this is a good assumption, but to our so the analytical shape of the gravitational signal has nothing to do with the equipartition assumption.
So you mean that this blue line is solely from velocity field, or magnetic field contribution is introduced?
You can have them both. Look, I will show you the formula. Just you have it in the backup. So this is the formula, okay? Omega gravitational waves as function of k and as at the final time of action of the source. And you see there is this quantity here, which is, I call it omega s. So omega s is the energy density in the source. With respect to the energy density, the radiation energy density in the universe at the moment of the source. And so this can be kinetic, or it can be magnetic, or it can be both. Okay, so it is really, and the spectral shape, since we are in any case talking about turbulence, and so we are assuming that both the kinetic spectrum and the magnetic spectrum are Kolmogorov. There is where indeed, no, then you're right. So in this sense, yes, we are assuming equipartition because we are assuming the same initial spectrum for both the kinetic and the magnetic components. They needn't be the same in amplitude, you see, but we assume that they are both Kolmogorov.
Yeah. Okay. Then the question would be that in your numerical calculation, equipartition seems all the lines numerical line. Do you mean that the equipartition is established, or do you have any suggestions that the equipartition might not be established?
I think so the results I showed in these particular simulations, so look, these are done with zero magnetic field. So this is purely kinetic turbulence. These are done with an initial purely magnetic field and zero kinetic. Okay, so these are really two distinctive features. Now, with the pencil code, so with the Scott's code, there is no magnetic field, so there is nothing you can do. With the pencil code, what they observe, this is not simulation, it is a simulation of other groups. What they observe is that equipartition is more or less always reached.
Okay, I see. But in this case, the magnetic field dominated case, and kinetic field. So in pencil code, if we start from purely kinetic energy, and the magnetic field amplification has not been observed yet. Do you know that?
So if you start with the purely kinetic turbulence in the MHD scenario, I don't think you don't get a magnetic field, right? Okay. So in the Navier-Stokes equation, if the magnetic field is not there to start with, you cannot produce it. Yeah.
I see. Okay, then so there will be some lower bound of the initial magnetic field coming from the transition Tame have studied. Like
absolutely.
That.
Yes.
Okay,
yes. You need to have a seed.
But you don't know what is the lower bound for the equipartition either. Okay, thank you very much.
No, it depends on what is your favorite magnetogenesis model.
Okay, thank you very much.
Okay, thank you. Guys, sorry, before we continue, since I see there are more questions, just to let you know that because we already passed time, let's consider this also the break where we can have a discussion, okay? And we certainly will continue with the other question, but just in case somebody wants to go for a coffee, so in this way, we will not get delay for the starting session after the break, okay? So having clarified this, please, Sebastian, go ahead.
Yeah, I'm wondering about the primordial black holes. So as you said, there's this window around the 10 to the 18 gram that could be promising. And you said that it's right, the frequency of LISA. So I'm wondering if LISA can close the window. So if LISA does not detect gravitational waves there, can it close this primordial black hole window?
It's a good question that no, I cannot really answer.
I can answer.
Yeah, so it depends on you see here they need to assume something in the inflationary curvature spectrum. right? And so I suppose that the mass is actually related to whatever they put in as a bump or as a delta function or whatever in the primordial spectrum. Right, so the amplitude here of this signal is related to the mass, which is then related to the model they put in by hand. So.
Just one comment, Chiara. So the mass is what determines the frequency because it has to do with the moment of horizon crossing of the fluctuations, but the amplitude is really just controlled by this AS or A psi parameter, okay, not related to the mass. So this what controls is the number density of these objects, and hence whether it can represent the total amount of dark matter, or if you put a smaller amplitude, then it would represent less amount of dark matter. You see, so answering Sebastian's question, yes, we could close the window because if you don't see this signal, it means that if there are primordial black holes at this window, they cannot represent the totality of the dark matter. Okay, and even though the answer depends, as Chiara pointed out, of some ansatz of the power spectrum, even more complicated. Typically, it's going to depend on the non-Gaussianity, okay, because this is a Gaussian approximation. In principle, for very reasonable assumptions, you always have a signal for the total amount of the dark matter being saturated by the primordial black holes at this mass scale, hence this frequency.
Okay, thank you, Danny. I was not prepared. Yeah.
Thank you both. Yeah.
Okay, more questions. Ali Younesian, please.
Hello, thank you for your talk. I have two questions. I don't know if the answers are yet uncovered or not, but my first question is that how can we fix the noises like laser noise and acceleration noise? This is the first question. And the second question is that let's assume that the conformal cyclic cosmology expands more in the upcoming decade, and then can we expect LISA to provide any countable data from the previous eon or not? Thank you. I will listen.
Okay, so the first question basically, so you mean how do we determine this curve, right? So here, this is the acceleration noise. This has been probed by the LISA Pathfinder. So basically, they have in the LISA Pathfinder, they have tested the ability to put a mass in free fall with a residual acceleration which is low enough to guarantee the gravitational wave measurement at this level of sensitivity. And so this is now, I mean, okay, obviously LISA is not the LISA Pathfinder, is going to be more complicated. There are 3 spacecraft, etc. But more or less, this is now settled. And here, this is the laser noise, right? So this depends on the power of the laser, and it is also pretty much known. Huh? Does this answer your first question?
I think yes, because I didn't know from the LISA Pathfinder results. And what about the clock noises?
Clock noises, yes, they are also somehow here. I mean, I don't know the detail basically, but I know that they will have some issues in synchronizing obviously all the clocks, and but I don't think this is a major issue in the noise balance of LISA.
Very good. So do you have any answers for my second question, or?
So what was it again?
Just let's assume that the conformal cyclic cosmology by Roger Penrose is true, and in the upcoming decade it expands more by the scientific scientists. I want to know that if can we expect any valuable and countable data from LISA to provide us for the CCC or not, before to understand anything coming from the previous aeon?
I don't think
I don't
so.
know if you know the CCC model or not, I don't know.
No, I don't see how. I mean,
very well.
no
Thank
idea.
you. Thank you.
So I don't know if you mean by probing, somehow probing the late time acceleration through standard sirens. Well, then I doubt it, because I mean, it is going to do whatever all other cosmological observatories do. LISA itself, it is within the solar system, so the metric is completely decoupled by anything else, right? So you don't think you see anything there between the lasers. So
thank you.
All right, thanks. Junichi Yokoyama, I think you can unmute yourself.
Yeah,
and
okay,
go ahead,
thank
please.
you. Yeah, I have just a comment about this view graph. So the relation between primordial black hole formation and stochastic gravitational wave background was first studied by Ryo Saito and myself back in 2009. So I hope you take a look at our paper.
okay, I will
the same conclusion.
rest. I will add the citation. Thank you.
Thank you.
Junichi, since you are here, let me take advantage of asking you a question, since this is now time for debate, because it's true you first pointed out this in 2009 in your paper 2009, but all of those computations, including the ones here, are based on assumption of Gaussianity of fluctuations, which allows you to break the 4-point function through Wick theorem into products of 2-point functions. And then here you introduce an ansatz now for this 2-point function, and this is what gives the different shapes. But in reality, the abundance, whether the primordial black holes can represent the totality of dark matter or a fraction of it, really depends rather on the non-Gaussian tail, right, of the distribution, no? Of the
that is true. But I actually disagree with describing the non-Gaussianity in terms of the FNL parameter for the case of primordial black hole formation.
Okay.
You know, because FNL of order of unity, for the case of the CMB, it's a very tiny correction.
Yeah.
But for the case of PVH formation, it's a huge correction.
Okay. No, but I wasn't arguing that non-Gaussianity is of the local type form.
Right. Yeah. Okay. Good.
I'm referring to. I'm just arguing that since the actual prediction of a stochastic background from second-order large scalar fluctuations relies on the 4-point function of these fluctuations, one needs to take an assumption of how to write this 4-point function. And
right, yeah, 4 point even higher. Actually, the nonlinear dependence between the Gaussian quantity and actual formation rate. Yeah, I also formulated some non-Gaussian formula for the PVH abundance in I think in '99.
Okay, and my question is, how would it impact into this gravitational wave background?
Actually, not much.
Not much. Okay. Okay, that I would like to understand.
Okay, good.
I would like to understand, but okay, thanks for the clarification.
Yeah.
Okay, well, guys, I think we have 10 minutes before we reconvene, unless the organizers want to set up later the start of the next session. Maybe the organizers won't take.
No, I think it's
okay.
Sebastian,
No, let's keep on schedule.
Yeah, I would agree.
Cool, excellent. So we are on a schedule. Feel free to discuss something, anybody, if you want for this. I mean, take the Zoom channel as a discussion room, you know, if you want, until we start at 4:30 local time in Central Europe. Maybe organizers want to start putting co-host Valerie and Alex Vilenkin, if he's connected already.
Yes, this is done.
Okay.
So
I see Valerie. I'm not sure.
I don't see Alex either, but it's quite early, I guess.
Is what? Sorry.
He's in US, so West Coast, right? Or
yes, but he's in the West Coast, no? So yeah.
Yeah, okay. So I think he will join maybe after the coffee break.
Okay, cool. Well, I'm gonna disconnect myself 5 minutes.
Yeah, hi Valerie. So if you want, you can already share the screen for a second just to see that everything is in order.
It does that. Do you see it?
Yeah. Yes, not full screen yet.
Yeah, but nearly full screen, right?
Yeah.
Yeah. If I do full screen, it doesn't get better because my screen, my monitor size is not like my monitor format doesn't match the Zoom format. And when I change the slide, right?
Okay. Yeah. I didn't know there was a Zoom format.
Well, yeah, right. I mean the square, like at least if you go to kind of full screen mode or like kind of speaker view mode, then you have the. I mean, I can show you what happens since we have nothing.
I think it's widescreen, so it will make it.
Exactly.
The vertical direction will be shorter, right?
Exactly. You see this now? It's not good.
It's still in the same.
It's the same for you.
No, nothing has changed. Yes.
Yeah.
This is mysterious. And if I do, okay, so now let's try it now, and I'm curious. If I do like this.
The same.
Same. Well, okay, then we do.
Can you change slides just to be sure that?
Yeah. Right. Now wait, but now is it full screen, right, for you?
No, it's the same, but maybe.
Then I'm not showing the right. Wait, then I'm not showing the right window. Then what do I need? Maybe yeah.
Okay, now we see what you mean. But yeah. this is really weird because it's not always like that.
Right. So I think this is bad. Let me do I think the other way is better.
It is some crazy aspect ratio.
Yes, exactly.
Like 1/2 or.
My monitor is very.
Oh, it's Linux. For sure.
It's not Linux.
It's not Linux?
No, okay. I mean, it is Linux, but the problem is not Linux.
No. Of course, the problem is Zoom on Linux. Like, it seems they don't maintain that so well.
Yeah, that could be. Okay.
At some point, I made an update, and then Zoom just didn't work anymore. Like, it crashed on start, and then. Yeah.
Okay, so now you see this, and you see when I change slides, right?
Can you change them?
I did.
No, we cannot see. Sebastian, that was very thoughtful of you to start this process now.
Okay, wait, what's going on?
I must say we're still streaming on YouTube, but if you want to cut this out, we can do this later.
No, okay, I think I see what happens. I have the thing open twice. And this is probably the one I'm sharing.
Now we see.
This is the wrong talk. Okay, this is
yeah.
This is it. Okay. Wait, let me start over. Good that we have it all on YouTube. Yes. You think I've never done a talk on Zoom, right?
Yeah. Is this your first talk on Zoom?
Yeah.
Which Linux are you using? Ubuntu. Strange. I think Ubuntu should work. I mean, this is the most common one. Okay, so
now you see, and now I change the slide, and it changes, right?
Yes, perfect. Yeah, now we see that the window is active actually because yeah. Now I would need to ask which Linux because this orange cross on the top right corner. Before it was not active, so.
Okay. I suspect that I had the talk open twice and was sharing one and was
Yes.
changing slides in the other.
Well.
So can keep getting with the discussions. What is lush green? It's the name of the windows.
All right, then you'll see this the whole time. I think this is the name of the original template that I used at some point ages ago, and which since I have changed the color 5 times, so there's nothing green about it anymore.
I actually never know how this name is created, because sometimes in LaTeX, like whatever the name of your file is, the name of this PDF will be different from the name of the file. And I don't know how, I still haven't figured out how this works.
Isn't there some property like title or something like that's not the title that you see, like there's some yes, I don't know, some string that you can set for like I don't know, or something like title, or like in the, yeah, I don't know.
Yes, maybe, but I think it's not. It's somewhere. It's not just directly in LaTeX file. It might be hidden in some. I mean, yeah, you can set up it there, I guess. But then, even if you delete it, it could be stored in some auxiliary files and propagate.
Sorry, can I humbly request to make me a co-host?
Ah, good morning.
Yeah.
Need to make anyone else.
Yeah, it's done. Thanks.
Yeah. This time it was from the first attempt.
All right, it's about time, but I guess we can wait 1-2 minutes still to see if some people rejoin after a small coffee break. Everything is working fine, no? Because I was hearing you guys were having some fun with the size of transparencies. Everything is under control, I assume, no?
Yes, everything is under control now.
Okay, cool. Okay, 1 more minute and then we go. So we'll do, in case you were not in the previous talks, I don't know, Valerie, we'll do in after 30 minutes since you started, I will let you know, and then you decide if you want to finish then or keep on talking, but at the expenses in principle of time for questions, okay?
Yeah, no, I should be hopefully well within time.
Excellent. Okay, I guess we can start. Well, welcome back, everybody. It is a pleasure to have now Valerie Domcke. She's a leading physicist in particle physics and gravitational waves from the early universe. And well, she's gonna tell us something very interesting, which is how to probe GUTS, grand unification, with gravitational waves. So please, the floor is yours, go ahead.
Yeah, thanks, Danny. Thanks for the nice introduction, and thanks also to all the organizers for organizing this great workshop and inviting me. It's really been super interesting. So what I want to talk about today under this title is basically going to be about cosmic strings. So we'll also match on then nicely to the subsequent talk. And this is work done largely together with Wilfried Buchmüller, Hitoshi Murayama, and Kai Schmitz. And the outline of today, there will be two main parts. So I will first introduce the topic of metastable cosmic strings, and I will then come to look at the gravitational wave signal of these metastable cosmic strings and how we can use that to learn something by gravitational wave observations, learn something about very high energy scales, for example, a scale of band unification. If there's time, which I doubt very much, I'll also say something about kind of concrete particle physics motivations for these types of constructions. So to start with, just very briefly recap the basic picture behind cosmic strings, which is an old story. So cosmic strings are one-dimensional topological defects formed in a phase transition in the early universe. And in particular, the phase transition, to form cosmic strings, the phase transition has to be such that you break from some large gauge group G to some smaller gauge group H. Well, it doesn't a priori have to be a gauge group. You break from some group G to some group H. And then you produce cosmic strings if and only if the mapping of this vacuum manifold onto real space has certain non-trivial features, which in mathematical language means you produce cosmic strings if and only if the first homotopy class of this quotient group G over H is non-trivial. So what does that mean? In the simplest case that you can imagine, think about a U1 symmetry, or an SO2 symmetry. You break this via some Higgs mechanism, and now you can imagine that in different parts of space, the Higgs wave takes values around this rim. And if you kind of project this onto a slice of real time, you can imagine kind of the Higgs wave pointing outwards everywhere. And if you take different stacks of these slices in space, then you kind of find these one-dimensional topological objects, cosmic strings. And once you form such cosmic strings, they can evolve. They in particular evolve via self-intersecting or intersecting other cosmic strings and splitting off little string loops. And these string loops can now oscillate and they can shrink by emitting particles and gravitational waves. And this is in principle the only energy loss mechanism for these standard topologically stable cosmic strings. Because apart from this, there's kind of, because the strings are topologically stable, they don't have any inbuilt decay mechanism. So now let's look at a slightly more complicated scenario. And let's not just break a single U1 symmetry, but let's consider embedding this U1 symmetry breaking into the context of the standard model and grand unified theories. So we could consider, for example, the breaking of SO10 down to the standard model across a U1 symmetry, which could be, for example, B minus L, a U1 symmetry, baryon number minus lepton number. And then we break this group down to the standard model. And now we can apply what I told you on the previous slide, so we can check in this lattice symmetry breaking process, do we generate cosmic strings? And here, essentially, we're just breaking a U1 symmetry, so it's exactly the case I was telling you on the previous slide, and this is the prototypical example for generating cosmic strings. Now we can, however, also just look at the entire process all the way down from SO10 to the standard model and check if the first homotopy group of SO10 over the standard model is trivial. And this takes a bit more work, right? But you can compute or you can look it up. And this is in fact trivial, indicating that there should be no cosmic strings formed. But this is strange, right? Since I told you that cosmic strings are topologically stable. So how can it be that kind of in this sub-breaking process, you generate a cosmic string, but in the total symmetry breaking chain, somehow there's no cosmic string? And this was pointed out actually long time ago. And also the resolution to this is known since a long time ago. And the resolution is that you do form cosmic strings, but they are not topologically stable. So in particular, in this first symmetry breaking process, you generate a different type of topological defects. You generate monopoles, so zero-dimensional topological defects. And in the second symmetry breaking process, you generate the strings. So you would generate this gas of monopoles, then you wait some time, you generate the strings. The strings would now attach to the monopoles, or the monopoles will kind of chop the strings in little pieces, meaning that as soon as you generate the strings, they connect to the monopoles, and everything just kind of radiates away into gauge fields, into particles, into gravitational waves at the point in time when you generate the cosmic strings. And so hence there's nothing of this left over to observe in the early universe. And this is the scenario of kind of a string gas network discussed already in the 80s and 90s. Now, the maybe more interesting scenario from the point of view of an observational point of view is if you have in between these two symmetry breaking phases, you have a phase of inflation, cosmic inflation. Because then you would generate the monopoles, cosmic inflation can dilute them away so that you have not a single physical monopole in your universe. Then you generate the cosmic strings. Cosmic strings now find no monopoles, right? So they appear to be stable. However, in your quantum field theory, you still have the presence of the monopoles, so you can generate them via non-perturbative processes. You can generate them, you can nucleate the monopoles along the core of the strings with a rate which will be exponentially suppressed by the mass ratio, kappa here, of the mass of the monopole over the string tension, which is basically the ratio of the two symmetry breaking scales in this process. So what this gives you is cosmic strings which are formed and can then have an exponential long lifetime. So they can have lifetimes comparable to the age of the universe or even longer, but they are fundamentally not topologically stable. And that changes the standard picture of the evolution of the cosmic string network. And as you see, I don't have to go to very exotic example to find this type, right? Kind of, if I look at kind of realistic gut breaking chains, this actually happens quite a lot. At least that you form different types of topological defects, right? If you then can arrange for a phase of cosmic inflation in between, is a different story. That of course is kind of model dependent. Okay, so what does this mean? So it means that at early times we have a cosmic string network which just obeys the usual laws of cosmic string network because it is apparently stable. So I will have long strings, they can self-intersect, they can form loops. The loops can oscillate and emit, in particular, gravitational waves. And then at some time scale, which is given by this gamma d, so this is decay rate due to the monopole production, right? This is this guy. I can start producing monopoles on my strings. This will cut the loops, it will cut the long strings, and I will end up with segments, which could, either this segment could either originate from this loop, or this segment could originate by cutting this long string, where long string here means, kind of larger than the Hubble horizon, so kind of crossing your Hubble horizon. Or I could also still have loops which simply survive because, there's only a certain probability with which I start chopping the loops into little bits. So I now need to kind of track the evolution of this network beyond what is done normally to kind of include these types of processes. And to do so, what I will use is kinetic equations. So very generally, I can describe the evolution of a number density of certain objects, could be string segments, could be string loops, by some source term, which will depend on what object I'm looking at and in which epoch I'm looking at it. Then I need to account for, since this is the number density at a given time and a given length of the object, I need to account for the change in length that this object might undergo due to processes it experiences. And then I need to take into account Hubble expansion, and I need to take into the account that this object with a certain probability can decay because of the production of monopoles. So I can now solve these types of kinetic equations. And to do so, I need initial conditions. And the initial conditions I set in this area here, where the strings are still perfectly stable, and the loop network, or the string network is to some extent very well understood. So to some extent very well understood, what I mean is that we'll be basing our results on the Nambu-Goto model, where you simulate strings as strictly one-dimensional objects, in which case there's analytical formulas and also kind of numerical ladder simulations of how these networks evolve. And we can use that to then initiate our kinetic equations, which describe the later regime. So this is based, for example, on this paper here, for this early network. Sorry, no, sorry. This paper, sorry, this was incorrect. We're basing it on the usual kind of Mambo-Goto papers for this early network, and this paper here is one of the first papers which kind of starts describing this process of monopole production. I'll have the reference for this later. This is the reference. Okay. Now, to give you a concrete example, what does that look like? So I can look, for example, at the number density in loops. In this case, this is again just a general equation from the previous slide. In this case, this function here, which indicates that the change of length of a loop over time, is simply given by the gravitational wave emission. So the loop will emit gravitational waves with a certain power gamma. G here is Newton's constant, mu is the string tension. And due to this emission rate, the loop will shrink, and hence I will get a change in the length in every time step. The source function in this case is the loop production function. This describes how kind of loops are formed by chopping them off the long strings. And this is basically at times earlier than when the monopole production sets in. This is what this theta function accounts for. This is exactly kind of the loop production function, which is known from the simulations of the stable strings. And now I have these kinetic equations, and I can actually solve them analytically. So we don't need to run any simulations here. We can just solve these differential equations, and we get solutions for the number density in loops before the time that the monopole production becomes efficient, and then matching onto that for the time after the monopole production becomes efficient. And as expected, in this early time, you just produce, of course, what you already knew from the stable network. And at late times, you get an additional exponential decay function simply because the loops can decay into due to the production of monopoles. So this is pretty much as expected. A bit more complicated is the situation for the segments. So also for the segments, you have to take into account that they can shrink by emitting gravitational waves. In particular, in principle, the amount of gravitational waves that they radiate could be different, which is why there's a gamma tilde here instead of a gamma. However, in practical purposes, this is simply not known really, right? So for practical purposes, we will simply assume that the radiation from the loops and the segments has the same total emission power. And then for the source term, we now need to take into account that I can form a segment either here by chopping one loop in half, or I can get a segment, or actually two segments, by chopping a segment in half. So it's kind of feeds into itself and gets also fed from the loop production function. And again, this gives me a differential equation which I can solve. In particular, at early times, I will have no such segments, right? Well, segments is really identified as kind of a string which is not a loop, but which both endpoints of this string are occupied by monopoles and which is inside the Hubble horizon. And then at late times, I start to populate my segment function, and it is sourced in particular, fundamentally sourced by the loop function itself. And you can continue this for kind of all types of different sorts of objects. For example, the segments that you get from the long strings, you can do the same sort of analysis. Okay, so now we understand how what equations govern the evolution of this cosmic string network, and what is the difference compared to the stable strings. Now we can use this to compute the gravitational wave signal originating from such a network. So the general formula is as follows. So you want to compute the spectrum of the gravitational wave, so the energy density per logarithmic frequency interval. Okay, you have a prefactor which depends on the Hubble rate today, has a frequency factor, and again has here the Newton constant and string tension. And then the interesting part happens here. So here PQ is the power, for example, for the case of loops, this will be the power of a single loop, where this Q indicates the harmonic in which this loop is oscillating, and I need to sum, in principle, over all harmonics. And the CQ counts how many loops do I have oscillating at this harmonic, which emit gravitational waves at some point in time in cosmic history, such that I observe them today at some frequency f, which is the f that I have on the left-hand side of my equation. So this is a very indirectly defined object. In order to compute it, I need to do an integral over redshift, and I need to know the cosmic history here in the denominator, and I need to know the number density of loops at any redshift with any length and any time, where the length of the loop is directly related to the frequency at which it emits, modulo the harmonic at which it emits, this relation here. So what we obtained in the first part of the talk, we obtained precisely equations governing these number densities. So I can now take these number densities, plug them in here. Cosmic history, I assume I know. And then I can compute the power spectrum of the gravitational waves. I should say that there is some uncertainty also in this blue object, right? In the power spectrum of a single loop. So here we use a simple formula here that you can like vary this a bit, but like that won't kind of dramatically change. It depends kind of if you look at cusps or kinks or whatever on the loop, but this kind of won't dramatically change the results. So now we can do this, right? So we plug in the number density, which, you know, as I just showed you, is typically kind of, for example, here for the number density of loops would be the usual number density for this obtained from the stable strings times this exponential suppression, which is effective at late times and indicates the decay of the loops. And I need to kind of do the same story, not only for loops, but also for the segments. And at the end of the day, plugging in all these results, I then obtain finally my spectra. So what I'm showing here, left is loops, a contribution from loops, right is contribution from segments. In general, I will have both, so if the sum over both contributions. And I'm showing the energy density, so omega gravitational wave, as a function of the frequency. These solid gray regions are existing experiments. The light gray regions are proposed experiments, or planned experiments, I should say. So that's SKA, there's LISA, and there's the Einstein telescope. And these colored lines are now the predicted signal, where the different colors indicate different values of G mu, so the string tension. This is directly related to the symmetry breaking scale of the U1 symmetry. And the difference between the solid and the dashed lines are different values of kappa, where kappa, I remind you, was the ratio between the monopole mass and the string tension. So basically the ratio between the SO10 VEF or the SO10 breaking scale and the U1 breaking scale, right? And these are the only two parameters that I have in this model, right? I have two symmetry breaking scales, and that's the only parameters that I have. And here I'm varying both. And as you can see, varying the energy scale of the U1 breaking group gives me just an overall shift up and down. And then changing this kappa parameter changes the lifetime of the strings. So the smaller I make this parameter, the closer the two scales are in energy, meaning the shorter is the lifetime of the string and the more suppression I get at low frequencies. The suppression happens at low frequencies because low frequencies are sourced at late times. And if my string network decays, then I just don't populate those frequencies. So this is kind of very nice because it means, for example, what it means is that you can construct models where you have a suppression at low scales, but large signals at relatively large scales. So you could kind of avoid strong bounds coming from pulsar timing array and still get a large signal from LISA or LIGO or the Einstein telescope. So just one comment on the segment. So the segment contribution, I should note that I only have that if my monopoles have no additional unconfined flux, because if there's an additional gauge group which kind of attracts my monopoles, right, then that would be the main energy loss and not the gravitational waves. So this signal on the left will always be present. The signal on the right will not always be present. It also turns out that the signal on the right is always at least marginally smaller than the signal on the left. So it turns out in the end, for pheno purposes, the segment contribution is not actually super relevant. However, this is kind of something that we learned by doing the computation. I'm not aware of any argument that you could have kind of anticipated this from the start. Okay, and so here now I put everything together. So I add the loops and the segments. This gives me these colored curves, again, for the two values of kappa and for different values of G mu. And I also add in dotted black, I add what you would get for perfectly stable cosmic strings. So the limit of large kappa, like the square of kappa larger so than 9, then you get to the limit of stable strings, meaning a lifetime larger than the age of the universe. And here you see exactly this point I was making, that all these values of g mu that we're looking at here, which roughly corresponds, so 10 to minus 7, g mu time is 10 to minus 7, roughly corresponds to the Gutt scale. So all these large values were previously considered simply ruled out from bounds from pulsar timing arrays. Now you see that the bounds from pulsar timing arrays are still perfectly compatible with Gutt scale strings, if the strings are metastable and not perfectly stable. So this is exciting, but it also just means that it's huge discovery space for LISA, and it's discovery space for LIGO. So in principle, LIGO could see something tomorrow, and it would not be in contradiction to any other measurement, and it could directly tell us something about the early universe. Since I have the orange square here, so the orange square here is the hint from pulsar timing array, so the hint of a potential gravitational wave signal, right, which is not confirmed. It's not clear that it is gravitational waves, but you can see that kind of with these types of models, of course, you can, for certain parameter choices, get into the region where you could try and explain the pulsar timing excess noise with this type of signal. So let me just spend one slide on that. So here simply, I've just recasted the parameter space. So now I'm showing the amplitude and the tilt of the gravitational wave signal in the PTA band. So the orange lines are the nanograph hint, and the black lines are the Parkes PTA hint, where hint here means kind of they have excess noise. It's kind of common across different pulsars. It can be modeled by power law, but it's not confirmed that this is gravitational waves because they don't have the statistical significance to kind of see the spatial correlation that you would need to claim that this is a smoking gun for gravitational wave signal. So we need more data. But while we wait for more data, we can chase an ambulance. So these colored lines here indicate what you would expect in this metastable cosmic string model for different values of g mu, again, the colored lines, and different values of kappa, right? So along these dotted lines are lines for constant kappa. So this is basically the model parameter. This is the parameter space that this meshed region indicates a parameter space that we could cover within our model, where the region above here is simply excluded by the PTA bounds. And the region kind of overlapping with these hints is the region where, in principle, this is compatible with a gravitational wave interpretation of the PTA signal. But clearly, we need more data, also because even if it is gravitational waves, right, there's perfectly fine astrophysical explanations for gravitational waves in the PTA band. So this is something simply to wait and to observe. If I zoom out of this parameter space a bit, so now I'm showing it again in terms of the two model parameters. So I'm showing it in terms of kappa, which was the mass ratio of the two symmetry breaking scales, and g mu, which is the string tension. And these, again, I stress these are the only two parameters in this model. In this parameter space, I can now see where different gravitational wave observatories lie. So here in this corner, for example, we have, like, for relatively large string tensions and long living cosmic strings, we have an exclusion region directly from the CMB. Then we have regions excluded by pulsar timing arrays. I should say that this orange region is 2 years old, so it's before the nanograph hint was published. We have here a region excluded by LIGO, and then we have the prospective reach of LIGO and of LISA. And you can see that this really kind of covers, these gravitational wave experiments will cover a big part of this parameter space over orders and orders of magnitude in the string tension, meaning the symmetry breaking scale of the processes involved, and also, a reasonable amount in kappa. So this doesn't look much, right? Because we have exponential sensitivity in kappa. But also recall that in order for this mechanism to work, you need a phase of inflation between these two symmetry breaking processes. So you really can't make kappa order 1, because otherwise everything is kind of too squished. You're going to have a very hard time model building this. And okay, if you make kappa larger than 10, then you're just kind of back to stable strings. And that's the scenario which is excluded down to very low values of g mu, simply because of from the PTA bounds. And these of course will also improve. Right? I'm not showing the prospects for SK8 here, but this would of course kind of cut down into this region to the left here. Now what I'm showing here in this hashed region is the thing that I, as anticipated, will not have time to talk about. So this is with my PhD thesis from 10 years ago, where we had like a nice gauged U1 B minus L model, which could do inflation and leptogenesis and dark matter. And at the time, I didn't know about metastable cosmic strings. I just knew about stable cosmic strings, and I was very concerned that this all seemed very ruled out because you were kind of up here, right, for that stable cosmic string limit, where the CMB bounds really exclude this model. However, now I know that there's metastable strings, so this plot gets the second dimension. So this is kind of the range where this model would work, because it has a relatively fixed energy scale inbuilt. And so this is kind of an example for really a high scale leptogenesis and inflation model, which is very hard to probe otherwise, but here you can kind of completely exclude it already with the upcoming LIGO runs. And the PTA hint is just here, right? So there's some overlap. So I'm excited to see kind of what LIGO data and PTA data will give us in the next couple of years. So with that, I conclude. So the take-home messages are that we should not only think about topologically stable strings, but actually metastable strings are something, you know, which can happen pretty generically in gut-breaking schemes. And it's, I think, a very interesting target for gravitational wave observatories, in particular for LIGO and LISA, who should not be discouraged by the seemingly strong PTA bounds on cosmic strings. Yeah, maybe we've already seen them with PTA or not, right? But this is very, yeah, very speculative. And there are also, I didn't talk about this in any detail today, but there are really kind of good particle physics models, good early universe models, which, you know, work really, really well in this context, and which are testable using these types of signals. Thank you.
Thank you very much. Thanks a lot, Valerie, for the very nice talk. Now, questions. Okay, I see there is a first hand raised up by Kohei. Please, Kohei, go ahead.
Hi, Valerie. Thank you for the nice talk. So I would like to ask one thing that, so when we worked 10 years ago, we had several uncertainty of the gravitational wave spectrum from cosmic strings, such as the loop size or Namagoto or Abelian-Higgs discussions. So are these discussions be settled down, or it still have the under debate, and you decided to choose this model?
Yeah, excellent question. Excellent question. So yes and no. So I think there was two big open questions at the time. One was, as you say, the loop size, and one was even, do I use Namagoto or the Abelian-Higgs description, right? And the loop size is kind of really only a fundamental question within the Namagoto model, right? Because only there is it a free parameter. And so that question, I would think, is now relatively answered, because simply from simulations in the Namagoto framework, the loop size, they kind of seem to, as far as I can tell, kind of literature seems to be converging on a loop size of about 0.1 in units of the Hubble horizon. So to my understanding, this is no longer a big debate. So relatively, the loops are sourced at relatively large scales. Now, the questions of the Abelian-Higgs versus the Namagoto, I think, is unresolved to my understanding. So just to back up a bit on this, so the Namagoto model kind of describes things as very strictly one-dimensional objects. So it doesn't have any memory of the field theory, which was originally creating the cosmic strings. But then the advantage of this is that you can kind of, because then you really just have one typical scale, which is kind of the typical, say, scale of the network. So for example, the scale separation between the strings, then you can simulate this very well on a lattice. In the Abelian-Higgs model, you actually simulate the field theory, which is, you know, fundamentally what you want to simulate. However, then the problem is that you have two scales. You have the width of the string and you have the separation of the string, and in an expanding universe, they kind of start to separate, and you run out of lattice space to do that. That's my very non-expert simplified view of the picture. And so the two of them roughly agree for the long strings, for the abundance of the long strings. However, the long strings are not what is predominantly sourcing the gravitational waves. So if you put bounds directly on the long strings, for example, from the CMB, then you more or less get the same result in both cases. But if you look at the gravitational wave produced from the loops, you get very different results. And I think it's kind of, I suspect the truth is somewhere in between. And to my understanding, that remains an open question. I don't know if Danny has something more to say on the question.
No, you explained it perfectly well. All right, thank you. I see.
So in the update, so finally we do not find gravitational wave at the PTA, partial timing array. So it can be earlier decay of metaspheric cosmic string, or Abelian Higgs would be correct.
Or it can simply be there's no phase transition.
Yeah, absolutely. Okay, thank you very much.
Okay, excellent. I see Asier has raised up his hand. Please unmute yourself and go ahead.
Okay, can you hear me?
Yeah.
Okay, so my question is more in the process of the production of just these segments. So the point is that you initially have this a string network, and then suddenly you create monopoles on it. So my question is, are these monopoles created monopole anti-monopole, and that's the reason why you don't have two segments from each monopole, or which is the process in which you are removing some of the segments connecting all the monopoles?
Okay, so I think I always need to generate the monopoles in pairs, because otherwise, what would you do to the, like, how would the other end of the string look like? Right, the string cannot end in nowhere, right? So the string can only end on a monopole. Like a topologically stable cosmic string cannot end at all. So the only way I can cut the string is by creating a pair of monopoles. And if you call them now monopole and anti-monopole or monopole pair, depends a bit on if these monopoles are charged under additional symmetries or not.
Okay, no, because if you create just monopoles in the string, what you have is just a necklace, and then you are not going to be able to produce these segments. So you have to somehow produce it in, okay.
Right, yeah, there's also there's a necklace and there's also the dumbbells, right? And this, sorry, but yeah, okay. So in that sense, yes, I would say here I'm producing monopoles and anti-monopoles, and I'm really kind of cutting my string using these.
Okay, thank you very much.
Thanks. I see there is a Mudit Jain. Please unmute yourself and go ahead.
I can't hear you yet.
Mudit, can you unmute yourself if you want to ask a question? We see you mute. Did you raise up the hand by accident?
Okay. Otherwise, you can also post it in the chat, and then I'll answer afterwards.
Right. Yeah. Okay. So no action from Judith. So maybe I can go ahead. So I have a comment and an observation, Valerie. The comment is also a question, but the comment is that when you assume the production of gravitational wave radiation from segments, you were assuming similar gamma, and this is hard to take, because the actual value of gamma, which is, just a mean value from simulating and having many loops in an Nambu-Goto simulation, it really comes from the structure of the formula on what the whole emission gravitational wave from Nambu-Goto is based on, which is the famous formula by Weinberg for isolated weak sources periodically oscillating, which is the case of loops, but not of segments, so it's hard to believe that you are going to get similar numbers. Being naive or without any real insight, I would really speculate that it has to be much smaller, the emission. That's what I would, the power itself per segment, I would rather think is much more suppressed. Not that I have a physical good argument, but certainly the formulas have, I don't think you can apply the same formulas.
Right. So let me just briefly comment. So we don't use, and then you can go for your second one. So we don't use, where's this here? So we do not use this formula, right, for the segments.
Okay.
This formula we only use for the loops, for the power of a single loops.
Yeah.
Rather, we use, and I don't think I have it here on my slides, but like there is a formula in this paper which gives the emission from the segments, essentially also for a given harmonic. The problem is if you sum now over all harmonics, in this case, for the loops, no, but in this case, you would get something which is UV divergent. So you need to kind of cut off this series at some point by some physical argument, right? And essentially we cut it, and this I think is yeah, I mean I totally agree with you, right? That this is really we don't know, right? I mean taking this gamma and this gamma tilde to be the same is simply because
I'll just give some number, okay.
But what you would physically want to do, you would kind of need to understand what cuts off this series, and then you would really get an answer for what is this gamma tilde. So we just do kind of what is done in literature, including this paper, right? We take them to be equal. But I totally agree with you that really we don't know, and this is also why I think that kind of computing the segment spectrum, despite that then at the end it is numerically, in this case, not significant, I think is kind of important, because if somebody comes along in a few years and tells me, you know, this gamma tilde is larger or smaller, you know, then we have the computation and can easily scale the thing. But I very much agree, and it would be fantastic if somebody could do a number-go-to simulation of this and answer that question, because yeah, I think that would be the way how to do it.
Something curious is that there are harmonic emission in first place, because the harmonics in the loops have to do with the fact that they oscillate periodically, you know, and if you have a segment here, unless it's rotating periodically, it's not even clear to me why there should be any series of harmonics and not just arbitrary continuum frequencies, you see.
Yeah, I mean, it is related to the length of the string, right? So that it kind of you can oscillate in units of the inverse units of the length of the string.
Okay, well, I don't know this paper, so I'll have a look offline. Thank you. Okay, then if there are no more questions, I have another question myself. Yes.
Sorry, I was unable to unmute earlier, but I think I got it to be working now.
Who is speaking, Mudit?
This is Mudit. Yes.
Yeah, go ahead, Mudit.
So, sorry about this. But I had a very naive question. Great talk, by the way. Thank you so much for the talk. So I think my question is mostly relevant for long-lived strings. So, you know, strings that can survive, let's say, till a redshift of 0 even, or 1 or 2, whatever. So how, and the question is, I think, also relevant only for PTA constraints. So how sensitive are the PTA constraints to, you know, these long-lived strings, and in the sense that how sensitive is the gravitational wave production for, you know, from strings which okay, in your plots you had the gravitational wave emission only up until like in the radiation domination?
No, this is we have the full thing, right? So here you see the entire cosmic history, right? And so some of the analytical formulas I was showing you earlier were just for radiation domination, just for simplicity. But we have analytical formulas for the entire regimes. And in fact, here in these dashed black lines, which are the stable strings, this bump and this fall off that you see here is precisely due to matter domination. So the plateau part of the spectrum is radiation domination. The slight change from the plateau is because change of degrees of freedom, but this plateau is radiation domination, and then here you enter matter domination.
I see. So then how much do you think it would be, you know, because these things can get captured, and you can have, you know, like in our local galaxy, we can have more strings as usually would have thought, you know, just from matter domination calculation because of capturing of strings. So you get a local overdensity of strings in a halo or something. How much do you think, you know, that would affect these constraints?
Well, I mean, depends on your local, but I mean, okay. So here you have, okay, you have the long strings and you have the loops, right? And the long strings are not, in the Yamamoto model, the long strings are not actually dominantly contributing to the gravitational spectrum. So you're looking at the loops.
Yeah.
And then you
right,
have
I'm thinking of loops, yes.
Then you have loops of all sorts of different sizes, right? Yeah. And I mean, the loops which are recently formed are large, right? Like really large, like horizon size large. Today, of course, you cannot capture in a galaxy, right? So I guess the question is the small loops, right? And so you would need to kind of check if you know, loops which are small enough to undergo the effect that you mentioned, how much if you add some local overdensity factor, how much that would affect the spectrum. I would honestly, yeah, I don't know. I would kind of suspect not terribly much, right? Because kind of the very, like this transition here, this peak is matter radiation equality, right? So kind of deep in matter domination. Now you're even talking really about kind of today, right? So vacuum domination. You're really here on the left. So I suspect that the effect is not huge, but I don't know. But we have, in principle, I think we have all the formulas that you could compute this, because we have all the formulas, you know, for the number densities, and in principle you could add and how that enters into the gravitational wave spectrum. So you could simply, well, I mean, not us, right? I mean, this is for the stable strings. This is known since a long time. You could, in principle, just kind of, you know, modify that number density as a function of the length and the time in a way to capture your effect, and you could see how that modifies the spectrum.
Yeah. Okay. Thanks. Yeah, because the reason I asked that was because at some point we did look into, you know, how much the strings would be captured and so on and so forth. There have been works by Chernodub and company, and then you know, some work by us. Alex, I think, is also in the talk, so he might also know what I'm talking about. But I've also been trying to look into, you know, what this effect of local capture, local overdensity of the strings would be on specifically PTA measurements, because my understanding was that the way that you get, you know, constraints from PTA is that you're just looking at, let's say, different pulsars that you have all around the sky, and then you're just correlating them and seeing how much variation you see in the timings. And so my naive thinking was that it would be dominant if you have some local overdensity of strings, then the gravitational waves that they're producing, you know, in recent times, that would be the most dominant effect, or the most dominant, you know, cause that would lead to these variations in the timings of the pulsars. So that's the reason that I'm trying to understand this question. But
right.
thanks a lot.
Then you would essentially be looking for, right. I mean, so this plot that I'm showing, right, you're right. I mean, this is implicitly assuming just kind of an isotropic stochastic background.
Exactly.
Right? But you could, of course, look for, in particular, for kind of strings at late times, right? You can look for bursts, gravitational wave bursts from the strings, and you can look for anisotropic signals. Yeah.
All right. Thanks a lot. Thanks a lot.
Okay, thank you. I still have my question, and even another question came to my mind, but I think either I can ask you later on or in Geneva this summer, because there's been plenty of questions. We are still on time because you really gave your talk pretty much on time, even shorter than the time expected. So, well, let's thank Valerie again. Thank you very much. And then we move on into last talk of the day. Alex Vilenkin, please, if you are around, feel free to start sharing your screen. Hello, we see you now there.
Yes, you must be a co-host, so sharing should work.
Let's see. Yeah, I don't see.
Do you see the menu of options at the bottom of the Zoom window that says security?
I see it says share screen. I'm clicking on that.
Yeah.
But I don't see my my screen there.
Okay.
But maybe you need to give some permissions.
So what kind of permissions do I?
Well, it depends. So if it is a new computer, for example.
No, it's not a new computer, and it's
okay.
it used to work before, but oh boy.
Yeah.
Yeah, another option could be reconnecting somehow this.
Yeah, maybe you want to switch off Zoom and then reconnect again, just to see by luck that.
Switch off Zoom?
Just to switch off and then reconnect into Zoom again, yes. Just to see if.
Okay, so I kill this window?
Yeah.
Yeah, so leave the meeting maybe before.
Okay, leave the meeting.
So Danny, you have time for a question.
Well, it's 2 questions, but you know, we would need the plots, so it's okay. We postpone. Just in case Alex comes right ahead.
Sure.
Well, one of the questions I can do without the plot. Meanwhile, we wait. So, Valerie, in your predictions, you were showing now how there is this nice bending in the lower frequencies that allows you to avoid PTA constraints for even very high G mu's. And if I got correctly the info in the plot, the G mu of order 10 to minus 7, which is borderline with compatibility with CMB, it's however the one that somehow was crossing PTA PTA announcement of a noise, no, whatever it is. Well, sorry,
okay.
Alex is here.
I'm back, but hopefully it will work. No, it doesn't work.
Now I made you a co-host, so you should be able to share.
So now you made me a co-host?
Yes, yes.
Yeah, I don't know.
So what happens? So you click.
It says Microsoft PowerPoint unknown. I don't know what.
Can you share the whole desktop?
How do I do that?
So if you click screen share, in principle, the first options are usually this desktop, not a specific program, but the whole desktop.
Yes, screen. So it's in the top left corner, and it's called screen.
Sorry. So do I click on share screen or not?
Yeah, you click on share screen.
Yeah, I clicked on share screen, then it says desktop.
Desktop is great, yeah.
Huh?
Desktop is great.
Desktop is good. Then you will share.
Then we see your whole desktop, whatever you show on your desktop, and also your presentation.
The whole computer, whatever you have there, yes.
Allow that because allow.
Yeah, you have to allow. So that's some security feature.
Okay.